Hello there and welcome to Science for Sleep, where we take some of the strangest ideas in science, give them plenty of room to breathe, and explore them slowly enough that you can follow along without feeling as though there will be an exam at the end. Tonight, we're looking at a question that sounds as though it escaped from a science fiction film. Have we finally found a real wormhole? Not built one, not photographed one, not sent an unfortunate volunteer through one while several scientists stood nearby holding clipboards. Found one? Or to be more precise, have we already detected something that might have come through one? The story begins with a gravitational wave signal called GW190521. It arrived at detectors on Earth on May 21, 2019. It lasted only a very short time, and when scientists examined it, they found themselves dealing with something unusual. The standard interpretation is that two enormous black holes collided and created an even larger black hole. That explanation still fits the observations well, and it remains the conventional explanation for the event. But GW190521 has always been a slightly awkward member of the gravitational wave family. It is short, it is heavy, and unlike many black hole mergers, it does not give us a long, obvious inspiral in the detectors before the final collision. Instead, much of what we detect is concentrated around the violent final moments of the event. LIGO and Virgo described GW190521 as a short-duration gravitational wave signal, and under the standard binary black hole interpretation, the two objects involved were estimated to have masses of roughly 85 and 66 times the mass of our Sun, producing a remnant of about 142 solar masses, which is already enough to make GW190521 interesting, without adding a wormhole. But physicists, as you may have noticed, are rarely discouraged by something already being interesting. Occasionally they look at an unusual observation and ask the scientific equivalent of, yes, but could it be even stranger? And in this case, someone eventually did. A theoretical proposal published in 2025 asked whether GW190521 might be interpreted not as the direct signal from two black holes merging in our observable region of the universe, but as something much more unusual, a gravitational wave echo associated with a wormhole, possibly carrying information from a black hole merger occurring somewhere else, perhaps even in another universe connected to ours through a wormhole throat. The authors found that their wormhole echo model could produce a signal with a comparable signal-to-noise ratio, although their statistical comparison still slightly favoured the standard binary black hole explanation. That distinction is important. We have not discovered a wormhole. GW190521 is not accepted evidence that another universe sent us a message. Nobody at LIGO opened the data file, saw the words "Greetings from Universe Number 2", and immediately began rearranging the physics textbooks. What we have is something much more cautious and in its own way, more interesting. We have a real astronomical signal. We have an established explanation that works reasonably well, and we have an alternative theoretical idea asking whether a wormhole could imitate some of the features that we actually observed. That gives us something physicists do not always have when discussing wormholes: data. Usually wormholes live almost entirely in equations. They appear when physicists take Einstein's theory of general relativity, explore the different geometries that spacetime might allow, and discover that the mathematics contain some very peculiar possibilities. One of those possibilities is a bridge. Imagine two regions of space-time that appear completely separate if you travel between them normally. Perhaps they are separated by billions of light years. Perhaps, depending on the model, they are parts of entirely different universes. Ordinarily, going from one region to the other would involve crossing the enormous distance between them. A wormhole changes the geometry. Instead of travelling all the way through ordinary space, there may be a much shorter connection through space-time itself. The popular illustration is a sheet of paper. Put one dot on one side and another dot far away. If you remain on the surface of the paper, the shortest path runs across the sheet, but fold the paper until the dots touch, make a tunnel between them, and suddenly the distance through that tunnel is tiny. it is a useful picture. It is also responsible for generations of people believing that physicists spend a surprising amount of their working day folding stationery. Real space-time is considerably more complicated. Still, the basic idea survives. A wormhole is a geometry in which regions that appear distant through ordinary space are connected by another route. And that possibility did not begin with modern science fiction. It grew out of general relativity itself. Einstein's equations do not simply tell matter how to move through a fixed cosmic arena. They describe how matter and energy influence the geometry of space-time. Mass changes geometry. Energy changes geometry. A black hole is one dramatic consequence. Once physicists realized space-time could bend, stretch, curve, and develop horizons, it became natural to ask what other shapes the equations might permit. In 1935, Albert Einstein and physicist Nathan Rosen studied a construction that became known as the Einstein-Rosen bridge. It is one of the ancestors of the modern wormhole idea. But before anyone begins packing sandwiches for a journey through one, there is a problem. The original Einstein-Rosen bridge is not the convenient doorway that science fiction travellers usually need. It does not simply remain open while you stroll through from one side to another. The geometry closes too quickly for ordinary travel. It is rather like discovering that your house technically has a second front door, except that the door disappears before anything can reach it. This led physicists to ask whether some other type of wormhole might remain open. And that question creates another problem. To hold open a traversable wormhole, many familiar models require unusual forms of stress energy, often described loosely as exotic matter, with properties unlike normal matter around us. Exactly what counts as exotic depends on the model, but the general issue is that ordinary matter tends not to cooperate with the geometry required to keep a wormhole throat safely open. Gravity, left to its usual habits, would rather collapse the structure. A stable wormhole therefore needs help. And physics becomes very interesting whenever a theoretical object requires an ingredient that nature has not conveniently placed on a supermarket shelf. Still, wormholes have refused to disappear from serious physics. Part of the reason is that general relativity keeps allowing geometries that resemble them under certain conditions. Another reason comes from quantum physics, and this is where tonight's story becomes considerably stranger. Because over the last several decades, researchers studying gravity, black holes, and quantum information have discovered that two ideas which once seemed unrelated may be connected. One is the geometry of wormholes, the other is quantum entanglement. Entanglement is the strange quantum relationship in which two systems can share a joint state so deeply connected that describing one independently of the other becomes impossible. It does not allow you to send an ordinary faster-than-light message simply by measuring one particle, despite what several fictional starship captains would probably prefer. But it does create correlations that have no comfortable equivalent in everyday classical physics. Then, in 2013, physicists Juan Maldacena and Leonard Susskind proposed an idea usually summarized by three letters, an equal sign, and three more letters. ER equals EPR. ER refers to Einstein and Rosen. EPR refers to Einstein, Podolsky, and Rosen, whose famous work helped frame the puzzle of quantum entanglement. The conjecture suggests, in broad terms, that wormhole-like connections and quantum entanglement may be two ways of describing something deeply related. That does not mean every pair of entangled particles contains a miniature tunnel you could crawl through. If that were true, quantum laboratories would need much stronger safety railings. The idea is more subtle. It suggests that the mathematics of space-time connectivity and the mathematics of quantum entanglement may be related at a fundamental level. In certain theoretical settings, what appears to be entanglement in one description can correspond to a geometric connection resembling a wormhole in another. And this has led to one of the more fascinating developments in modern theoretical physics. Wormholes are no longer discussed only as hypothetical shortcuts for spacecraft. They have also become tools for asking how space-time itself might emerge from quantum information. That changes the question considerably. Instead of asking only, Can something travel through a wormhole? Physicists can ask, could the connections we call spacetime have something to do with quantum entanglement in the first place? And if that sentence has made your brain quietly request a cup of tea, that's perfectly reasonable. We'll take our time with it. There is no need to understand quantum gravity before falling asleep. Most physicists would probably be relieved if somebody did. For now, keep one simple idea nearby. Wormholes may not merely be strange tunnels placed inside space-time. Some theories suggest that wormhole geometry could tell us something about how space-time and quantum information fit together at a deeper level. Recent work with simplified quantum systems has even explored dynamics mathematically connected to traversable wormholes. These experiments and simulations do not mean that researchers created a literal hole in space-time on a laboratory bench, and they certainly did not create a portal large enough to lose a set of car keys in. What they do show is that ideas related to traversable wormhole dynamics can be studied through controlled quantum systems, giving researchers a way to test pieces of the mathematics rather than leaving everything entirely on paper. Meanwhile, gravitational-wave astronomy has given physicists another tool. Instead of attempting to build a wormhole, perhaps we can listen for one. Gravitational waves are distortions in space-time produced by accelerating masses. When two black holes orbit one another, they radiate energy as gravitational waves. The orbit gradually shrinks. The black holes move faster. The waves increase in frequency. Eventually, the black holes collide. The newly formed black hole then settles down, producing a fading pattern of gravitational radiation known as ring-down. A typical waveform from a compact binary coalescence is therefore often discussed in three broad stages: inspiral, merger, and ring-down. You can think of it as a very brief cosmic performance. There is the approach, there is the collision, then there is the final vibration as the new object settles. GW190521 made that performance difficult to watch from the beginning. The objects were so massive that much of their earlier inspiral occurred at frequencies below the most sensitive observing band available to the ground-based detectors. What remained in the measured signal was short and dominated by the merger and ring-down region. Later analyses have continued to treat GW190521 as a particularly short merger-dominated event, with several competing interpretations of its details. That shortness matters. If you receive only the final bang and the fading vibration afterward, you have less information about what happened beforehand. Imagine standing outside a room and hearing a crash. If you heard footsteps approaching, furniture being moved, someone saying, "I don't think that shelf is secure," and then the crash, you would have a fairly detailed reconstruction available. If all you heard was the crash, you would have more possibilities. Perhaps the shelf fell, perhaps someone dropped a suitcase, perhaps a remarkably ambitious cat attempted something beyond its abilities. The sound is real. The event that produced it needs to be inferred. GW190521 gives us something similar, although involving curved space-time rather than an overconfident household pet. The standard black hole interpretation works, but because the signal is so brief, researchers have investigated alternatives involving unusual orbital configurations, eccentric mergers, gravitational lensing, exotic compact objects, and other possibilities. That makes it a useful place to ask a very speculative question. Suppose a black hole merger happened somewhere we could not normally observe. Suppose the remnant geometry involved a wormhole connecting that region to ours. Could part of the gravitational disturbance pass through the throat? Could it emerge on our side? And if it did, would we detect the full story? Or would we receive only a short pulse, detached from the long inspiral that originally created it? That is the basic motivation behind the wormhole interpretation proposed for GW190521. In that model, a binary black hole merger occurs in another region or universe connected to ours through a wormhole. The merger produces gravitational radiation there. Part of the post-merger signal interacts with the wormhole geometry, and an echo-like pulse emerges through the throat into our universe. We would therefore detect the final piece without having observed the ordinary inspiral leading up to it, which sounds suspiciously convenient. And scientists are quite right to be suspicious of convenient explanations. If an unusual observation can be explained by known astrophysics, that usually deserves priority over adding a wormhole in another universe. The question is not whether the wormhole story sounds exciting, it obviously does. The question is whether it produces a measurable signal that actually resembles the data. That is where the idea becomes scientifically useful. A hypothesis does not earn attention merely by being imaginative. It needs consequences, it needs numbers, it needs predictions that can be compared with observations. And when the proposed wormhole echo model was compared with GW190521, it was not immediately destroyed by the data. The model could reproduce important features of the short signal, but the standard binary black hole model remained statistically preferred in the analysis. A later paper by members of the same research line summarized the GW190521 comparison as favoring the ordinary binary black hole explanation over the echo model by a modest Bayesian margin, so we should keep both feet firmly on Earth, or at least as firmly as possible, while discussing inter-universe wormholes. There is currently no observational confirmation that GW190521 passed through a wormhole. There is no confirmed traversable wormhole. There is no confirmed gateway to another universe. But there is something valuable here. For a very long time, wormholes were primarily objects we could investigate mathematically. Now, gravitational wave detectors allow physicists to ask whether unusual spacetime structures could leave signatures that resemble real signals. Even a failed test teaches us something. If future observations become more precise, researchers can compare competing models more sharply. If wormhole echoes have a particular pattern, repeated events could reveal whether that pattern exists. If they do not, increasingly good data can restrict the range of wormhole models that remain plausible. Science does not always progress by finding the extraordinary thing. Sometimes it progresses by giving the extraordinary thing fewer places to hide, and that brings us back to the signal itself. GW190521 was detected by Advanced LIGO and Advanced Virgo at 3:02:29 UTC on May 21, 2019. The event reached the detectors after travelling across an enormous cosmological distance. Under the standard interpretation, it came from one of the most massive binary black hole mergers identified at the time, producing an intermediate mass black hole. For the detectors, though, the event was not a picture. It was not a flash in a telescope. There was no little black circle approaching another little black circle, while helpful arrows identified each object. The instruments measured incredibly small changes in distance as a gravitational wave passed through Earth. Laser interferometers watched perpendicular arms several kilometers long and measured changes far smaller than an atomic nucleus. From those tiny changes, scientists reconstructed events involving objects heavier than stars colliding billions of light years away, which remains a ridiculous achievement when you stop to think about it. Humans built machines sensitive enough to notice space-time itself stretching, and almost immediately began complaining that some of the signals were difficult to interpret. That may be the most human part of the story. Before we move deeper into what GW190521 might have been, I'd love to know something much simpler. Where in the world are you listening from tonight? And if you're already somewhere between awake and asleep, what part of this idea feels stranger to you? That wormholes might exist at all? Or that we may someday be able to detect one without ever seeing it? Perhaps you're listening in London while rain taps against a window. Perhaps you're somewhere warm with a fan turning in the background. Perhaps it is afternoon, and you have made the interesting decision to learn about hypothetical tunnels between universes instead of doing whatever you were originally supposed to be doing. No judgment here. The universe has been waiting roughly 13.8 billion years for you to procrastinate with cosmology. It can manage a little longer if you enjoy these slow explorations of science, and if they help you relax, learn something new, or simply give your mind somewhere interesting to wander before sleep. You can give the video a like and subscribe to Science for Sleep. It helps other curious people find their way here, and it tells the algorithm that there is apparently a demand for calm discussions about black holes, quantum entanglement, and the possibility that another universe might be knocking very quietly on our detectors. For now, get comfortable. There is no need to hold every name or number in memory. You do not need to remember the masses of the black holes. You do not need to memorize Einstein's equations. And should anyone unexpectedly ask you to derive a traversable wormhole metric before breakfast, I think we can all agree that they are being unreasonable. What matters is the question behind the details. We detected something real. We have a strong conventional explanation for it. To understand why that very brief signal became such a useful place to look for unusual physics, we need to go back to the morning it reached Earth and examine what the detectors actually recorded. GW 190521 arrived on May 21st, 2019 at 03:02:29 UTC. The signal was seen by both advanced LIGO detectors in the United States and by advanced Virgo in Italy. Together, the three-detector network measured it with a signal-to-noise ratio of 14.7, strong enough for researchers to treat it as a genuine astrophysical event, rather than an ordinary fluctuation in the instruments. And analysis designed to find more general transient signals estimated a false alarm rate of roughly one such event in 4,900 years. So there was little doubt that something had happened. The difficulty was deciding exactly what. Most gravitational wave signals from merging black holes have a recognizable structure. Two black holes orbit one another. As they lose orbital energy through gravitational radiation, they slowly move closer together. Their orbital speed increases. The gravitational waves rise in frequency and amplitude. Eventually the two objects merge, and the newly formed black hole settles down by radiating away its remaining distortions. GW 190521 offered only a small portion of that familiar story. The signal was exceptionally short and concentrated at relatively low frequencies. LIGO's own description called it shorter in duration and lower in peak frequency than the binary black hole mergers observed before it. A synthetic version based on the most likely parameters sounds less like the long-rising chirp people often associate with gravitational waves and more like a brief low-frequency blip. That brevity was not automatically suspicious. In fact, there was a straightforward reason to expect it. Massive black holes merge differently, from the perspective of a detector on Earth, than much lighter black holes. The larger the total mass of a binary system, the lower the characteristic gravitational wave frequencies around merger tend to be. A lighter pair can spend a comparatively long time sweeping upward through the frequency range, where LIGO and Virgo are sensitive. A very massive pair reaches its final stages at lower frequencies, meaning much of the earlier inspiral may happen below the detector's most useful observing band. By the time a system as heavy as GW 190521 becomes clearly visible to ground-based detectors, the black holes may already be extremely close to one another. It is the astronomical equivalent of arriving at the cinema during the final scene. You know a plot must have happened. You may even be able to reconstruct quite a lot of it. But you would feel more confident if you had seen the first hour and 40 minutes. Under the standard interpretation used by the LIGO and Virgo collaborations, GW 190521 came from two black holes, with estimated source frame masses of about 85 and 66 times the mass of the Sun. Those estimates carried substantial uncertainty, which is important because the signal itself contained relatively little information, compared with a long inspiral. The merger produced a final black hole of roughly 142 solar masses. Just pause on those numbers for a moment. Our Sun contains more than 99% of all the mass in the solar system. Now imagine something containing about 85 suns worth of mass compressed into a black hole. Place another black hole containing roughly 66 suns nearby. Then allow the two to collide. The resulting object was estimated to contain around 142 solar masses, with several solar masses worth of energy carried away primarily in gravitational radiation. There was no explosion in the ordinary sense, no shell of fire expanding through space, no sound wave moving through gas. The objects themselves were black holes. What escaped was a disturbance in space-time. That disturbance travelled across the universe, reached the Milky Way, passed through Earth, and changed the lengths of LIGO's detector arms by an amount vastly smaller than the width of an atom. A cosmic collision, involving more than 100 suns worth of mass, eventually announced itself here as an almost unimaginably tiny movement of mirrors. Physics does enjoy making the input and output look rather poorly matched. The final black hole was especially important because a remnant around 142 solar masses falls into the intermediate mass range between ordinary stellar mass black holes and the enormous supermassive black holes found in galactic centres. At the time of the announcement, LIGO and Virgo described GW 190521 as providing the first clear gravitational wave detection of an intermediate mass black hole, but the final black hole was only one part of the puzzle, one of the black holes that supposedly existed before the merger was awkward too. The heavier component, around 85 solar masses in the original analysis, sat inside a range associated with what is known as the pair instability mass gap. This requires a little explanation because black holes do not come with convenient labels telling us where they were manufactured. A sufficiently massive star reaches extraordinary temperatures and pressures in its interior. Under certain conditions, energetic photons can begin producing electron-positron pairs. That process removes some of the radiation pressure, helping support the stellar core. The star can become unstable. Depending on its mass and structure, the result may involve violent pulsations that remove large amounts of material, or a complete pair instability supernova that disrupts the star so thoroughly that no black hole is left behind. The details depend on stellar models, chemical composition, mass loss, rotation, and other ingredients, so the boundaries are not carved into nature with a ruler. Still, standard models predict a region in which producing black holes directly through ordinary stellar collapse becomes difficult. The original LIGO Virgo analysis placed the heavier GW 190521 component in approximately this problematic range and reported a 99% probability that at least one of the two components occupied the relevant mass gap under their assumed binary merger model. That did not mean an 85 solar mass black hole was impossible. It meant that making one directly from a single ordinary stellar collapse was difficult enough to demand an explanation. One attractive possibility is that the black hole had already been through a merger before. Imagine two smaller black holes meeting inside a dense environment such as a massive star cluster. They merge and create a larger black hole. That larger black hole remains in the cluster. Later, it encounters another black hole and merges again. You now have a second-generation black hole, one whose family history is considerably more complicated than the usual collapse of a single massive star. Black hole genealogy apparently becomes confusing very quickly. This process is called hierarchical merging, and GW 190521 immediately became interesting as a possible example, because hierarchical mergers provide a natural route for building black holes inside or above mass ranges that are difficult to populate through ordinary stellar evolution. LIGO and Virgo discussed repeated mergers, stellar collisions, dense star clusters, and environments around active galactic nuclei among the possibilities for producing such an unusual system. So even before anyone suggested anything remotely resembling a wormhole, GW 190521 was already unusual in several different ways. It was very massive, it was very short. Its inferred components challenged simple stellar formation expectations. Its remnant landed in the intermediate mass regime, and the limited amount of waveform visible in the detectors made reconstructing the system unusually dependent on the models used to interpret it. That last point deserves particular attention. A gravitational wave detector does not measure black hole masses directly. It measures a changing strain in space-time. Researchers then compare that measured pattern with theoretical waveform models generated using general relativity. Different masses, spins, orbital configurations, viewing angles and distances produce different gravitational wave patterns. If the signal is long, there can be many cycles available for comparison. Each cycle carries information. You can watch the frequency evolution. You can watch the amplitude evolution. You can examine subtle effects caused by spins. You can estimate how the orbit changes over time. With enough waveform in the detector, nature gives you many opportunities to check your answer. GW190521 gave scientists far fewer. The event was dominated by the merger and ringdown region, meaning that several different physical configurations could potentially produce signals that resemble one another during the brief interval that was actually observed. It is rather like identifying a song after hearing only the final two notes. If the song is familiar enough, perhaps you can do it. But several people in the room may produce different answers with impressive confidence, and at least one person will insist it was a song that nobody else has heard of. Researchers found that conventional waveform models describing quasi-circular black hole binaries could reproduce the observation. 3 waveform approaches used by the LIGO Virgo team, along with direct comparisons to numerical relativity calculations, gave broadly consistent source estimates. Tests focusing on the merger and ringdown were also consistent with general relativity. That is worth emphasizing because unusual does not mean unexplained. GW190521 did not arrive and break Einstein's theory. The standard merger interpretation works. The signal is compatible with 2 black holes merging according to general relativity. What made the event interesting was that the data were sparse enough, and the inferred system unusual enough, that alternative descriptions were harder to dismiss than they would be for a long, beautifully measured inspiral. One of the early questions concerned the spins of the black holes. A spinning black hole carries angular momentum, and when 2 spinning black holes orbit one another, the orientations of those spins can affect the binary's motion. If the spins are tilted relative to the orbital plane, the orbit itself can precess. Think of a spinning top whose axis slowly changes direction instead of remaining perfectly upright. In a binary black hole system, precession can leave characteristic modifications in the gravitational waveform. The original GW190521 analysis reported mild evidence for spin-induced orbital precession. But then another possibility appeared. Perhaps some of what looked like precession could instead be caused by orbital eccentricity. Most standard gravitational wave models assume that black holes approaching merger follow nearly circular orbits. There is good reason for that. As an isolated binary radiates gravitational waves over a long period, its orbit tends to become increasingly circular. By the time the black holes reach the frequencies measured by LIGO, much of the original eccentricity may have disappeared, but densely populated environments can complicate this picture. Black holes inside star clusters may interact with one another dynamically. A close encounter can create a binary that merges rapidly, leaving less time for the orbit to circularize. Such a system could reach the final collision with noticeable eccentricity. An independent analysis of GW190521 found that an eccentric interpretation could fit the signal, and that the available data could not confidently distinguish between eccentricity and spin-induced precession. The researchers demonstrated that a moderately eccentric system might be mistaken for a quasi-circular precessing one, and the confusion could work in the other direction as well. There was an even more dramatic possibility within ordinary black hole physics. What if the 2 black holes had approached one another on an extremely eccentric trajectory, perhaps almost a head-on collision? Numerical studies show that gravitational wave signals from head-on or highly eccentric intermediate mass black hole collisions could, under some circumstances, resemble signals interpreted using quasi-circular precessing merger models. Researchers specifically pointed out that this degeneracy could matter for GW190521. In other words, there was not necessarily one clean route from signal to source. The measured waveform was the evidence. The history behind it had to be reconstructed. This is an important distinction when discussing GW 190521 because it is easy to hear the phrase missing in spiral and imagine that scientists expected a long chirp, failed to find it, and were therefore left with a signal that black hole physics could not explain. That is not what happened. For a system this massive, a short observed waveform is not surprising. Much of the inspiral naturally occurs at frequencies too low for current ground-based detectors to observe well. The mystery is subtler. Because we do not see much of that inspiral, we lose one of the strongest tools normally used to distinguish among competing descriptions of the source. The black holes may have followed a nearly circular orbit. They may have been precessing. The orbit may have been noticeably eccentric. More complicated formation histories may have been involved. Researchers have even investigated whether the signal could be strongly gravitationally lensed, although the original collaboration analysis found strong lensing of a lower mass binary unlikely. Each proposal has to survive the same basic test. Can it reproduce the data, and does it do so better than the alternatives without requiring assumptions that are themselves improbable? This is where gravitational wave astronomy becomes less like simply listening to the universe and more like forensic science. The event itself is gone. No telescope can travel back to May 2019 and watch the merger from nearby. What remains is the waveform. From that waveform, researchers infer masses, spins, distance, orientation, and orbital behavior. The original binary interpretation placed GW 190521 at a luminosity distance of about 5.3 gigaparsecs with large uncertainty, corresponding to a redshift of roughly 0.82. By the time the signal reached Earth, whatever happened at the source belonged to the distant past. The black holes had merged, the remnant had settled, the gravitational waves had crossed an enormous stretch of expanding space. Then, for a fraction of a moment, Earth moved slightly differently. That was all we received. And yet, from that small disturbance, scientists could infer the existence of objects tens of times heavier than the Sun. There is something rather reassuring about the fact that the universe can be extraordinarily secretive and still leave paperwork behind. Gravitational waves are the paperwork. GW 190521 simply filled out the form rather badly. Its short duration meant that researchers could not watch a long progression from slow orbital motion to accelerating in spiral and final merger. Most of the useful information arrived near the violent end. Later ring-down studies have continued examining whether several vibrational modes of the final black hole can be identified in the signal. One analysis found that models containing multiple quasi-normal modes could reconcile ring-down estimates with broader inspiral merger ring-down models, while still leaving room for different interpretations involving precession or eccentricity. That word, ring-down, will become important. A newly formed black hole is not instantly quiet. Immediately after merger, its geometry is distorted. It settles toward a stable rotating black hole state by emitting gravitational waves with characteristic frequencies that physicists call quasi-normal modes. The easiest analogy is a bell. Strike a bell and it vibrates. The sound gradually fades as the bell settles. A newly formed black hole does something conceptually similar, except the ringing is not sound moving through air. It is space-time itself settling after an extremely violent rearrangement. The frequencies and decay times of those vibrations depend on properties of the final black hole. That makes ring-down enormously useful. It can tell us about the remnant. It can test general relativity. And importantly for where our story is heading, it gives physicists a very specific pattern to look for when asking whether something unusual happened after a merger. Because suppose the story did not end with an ordinary black hole quietly ringing down. Suppose the geometry near the source contained something else, a reflecting structure, an exotic compact object, a region where the usual boundary conditions around a black hole were modified, or, in the most radical version of tonight's question, a connection to another region of spacetime. Then gravitational radiation might behave differently after the main disturbance. Instead of simply escaping or falling behind an ordinary horizon, part of it might be delayed, filtered, reflected, or transmitted. A detector very far away would not necessarily receive a neat picture explaining any of this. It might simply record another short pulse. And that is exactly why a strange brief signal like GW190521 attracts so many interpretations. Not because it refuses to behave like a black hole merger, it does behave like one, but it gives us only a narrow observational window into what happened, and narrow windows allow more than one possible view. The standard binary black hole interpretation remains strong. The LIGO-Virgo analyses found the signal consistent with a massive quasi-circular merger and with general relativity. Nothing about GW190521 requires a wormhole. Nothing about it requires another universe. Even the unusual masses have plausible astrophysical explanations involving previous black hole mergers and dense environments. That is the baseline we need to keep in mind. Otherwise, it becomes far too easy to take every unusual feature and turn it into evidence for whatever strange object we happen to want before looking at the data. Physics generally prefers the opposite order. Start with the data. Ask what ordinary explanations can do, then determine whether anything remains that genuinely motivates something more exotic. G190521 earns attention because this process has been unusually interesting. Its enormous inferred masses raised questions about how the black holes formed. Its brevity limited the amount of orbital history visible to us. Its waveform allowed degeneracies between different possible configurations. Its ring-down encouraged detailed studies of the newly formed remnant, and its very existence demonstrated that gravitational-wave detectors could probe black hole collisions in a mass range that had previously been difficult to observe directly. There is also a useful lesson hidden in the event. A gravitational wave signal does not contain labels for inspiral, merger, and ring-down. Those categories are part of the physical model we use to understand the waveform. The detector records strain as a function of time. We provide the interpretation. Usually that interpretation is strongly constrained because general relativity predicts the full waveform with remarkable precision. But when only the final portion of a very massive system sits comfortably inside the detector's observing band, interpretation becomes more difficult. And before we can decide whether the missing earlier portion of GW190521 is merely the natural consequence of a massive binary, or whether anyone has a serious reason to imagine something stranger, we need to understand what should have been there in the first place. What does an ordinary black hole merger actually sound like to a gravitational wave detector? Why does the inspiral normally carry so much information? How do two objects that emit no light announce their approach long before they touch? And why, when the masses become large enough, does that long warning begin to disappear from instruments like LIGO and Virgo? An ordinary black hole merger does not begin with two black holes suddenly crashing into one another. Long before the final collision, the two objects are already locked together by gravity, orbiting their shared centre of mass. Depending on how the system formed, they may have been doing this for millions or even billions of years. During most of that time, nothing particularly dramatic would happen from our point of view. The black holes could be separated by enormous distances, circling slowly, losing only tiny amounts of energy. But gravitational systems have a problem. According to general relativity, accelerating masses can produce gravitational waves. A pair of black holes orbiting one another therefore sends energy away in the form of ripples in spacetime. Losing energy changes the orbit. The black holes move slightly closer together. Once they move closer, they orbit faster. Faster orbital motion produces stronger gravitational radiation. That removes more energy. The orbit shrinks again, and the whole process accelerates. This gradual inward spiral is what physicists call the inspiral. For a long time, the change is extremely slow. Then, as the separation decreases, things begin happening much more quickly. If you could watch the system from nearby, preferably from somewhere protected by an extremely generous insurance policy, you would see two dark objects circling faster and faster. Neither black hole has a solid surface. There is no glowing crust waiting to smash into another glowing crust. What you would really be watching is the motion of two regions of profoundly curved space-time. Around them, the surrounding geometry changes continuously as the objects orbit. Those changes travel outward as gravitational waves. A gravitational wave is not an object moving through space in quite the way a radio wave or a thrown tennis ball does. It is a changing distortion of space-time itself. As the wave passes through a region, distances in one direction are stretched while distances in a perpendicular direction are squeezed, and then the pattern reverses. The effect is tiny by the time a wave reaches Earth. Very tiny. The kind of tiny that requires several kilometers of laser interferometer and some of the most carefully isolated mirrors ever constructed just to notice that anything happened. Yet the source can be enormous. When two stellar mass black holes merge, they can briefly release more power and gravitational waves than all the stars in the observable universe are producing as light at that moment. And after crossing hundreds of millions or billions of light years, the resulting distortion reaching us may change the length of a 4-kilometer detector arm by less than a tiny fraction of the diameter of a proton. The universe is apparently capable of shouting at an astonishing volume while still requiring extremely sensitive equipment to hear it. The clearest way to understand the normal pattern is to think about frequency. Early in the inspiral, the black holes orbit relatively slowly. Each orbit produces a repeating gravitational wave pattern. As the orbit speeds up, the frequency of that pattern rises. At the same time, the objects move closer, the gravitational field becomes stronger, and the amplitude of the waves generally increases, so the signal rises in both pitch and strength. This is why gravitational wave astronomers often call these signals chirps. One of the best-known examples is GW150914, the first direct gravitational wave detection. Its measured signal swept upward from roughly 35 Hz to around 250 Hz before the merger, matching the pattern expected from two black holes spiraling together, merging, and leaving behind a single black hole. If the frequencies are converted into sound, the result really does resemble a short rising chirp. Although calling it a sound is slightly misleading. There is no giant microphone floating near the black holes. Space is not filled with air carrying pressure waves toward us. Scientists simply take the measured gravitational wave frequencies and represent them as audio frequencies so human ears can recognize the pattern. The actual detector is measuring changes in distance. Still, listening to the chirp is useful because the ear is very good at noticing changes in frequency. You hear the pitch climb. That climbing pitch is the orbit accelerating. Every part of the inspiral contains information. The rate at which the frequency increases depends strongly on the masses of the objects. In particular, gravitational wave physicists use a quantity called the chirp mass, a particular combination of the two masses that strongly controls how rapidly the signal sweeps upward in frequency. It is one of those names that makes physics sound almost disappointingly sensible. There is a chirp. It has a mass. Chirp mass. Nobody had to name it the transorbital relativistic frequency coefficient and make everyone miserable. If the two black holes are relatively light, their inspiral can spend a considerable amount of time in the sensitive frequency range of a ground-based detector. That gives researchers many cycles to analyze. Each cycle acts like another clue. Scientists can examine how quickly the frequency changes, how the amplitude grows, whether the orbital plane is moving, whether the black holes are spinning, and whether the orbit looks almost circular or noticeably eccentric. A long signal is useful for roughly the same reason that a long conversation tells you more about someone than hearing them say one word while leaving an elevator. The more waveform you receive, the more opportunities you have to distinguish similar possibilities. Mass is especially important because it changes the timescale of the entire event. Take two relatively small black holes. They can orbit at higher frequencies before reaching their final merger. Their signal therefore spends longer moving through the frequency band accessible to instruments like LIGO and Virgo. make the black holes much heavier, and everything shifts downward in frequency. The final orbits occur more slowly. The merger happens at a lower characteristic frequency. Much of the earlier inspiral can remain below the range where ground-based detectors are most sensitive. This is one of the central reasons GW190521 looks so different from something like GW150914. Its unusual brevity was not by itself evidence that the ordinary merger story had failed. A very massive binary naturally gives a ground-based detector less inspiral to work with. In a sense, the black holes have been performing the chirp all along. We simply enter the room late. During the inspiral, the black holes also reveal information through their spins. Black holes can rotate. Some rotate extremely quickly. When two spinning black holes form a binary, their spins may point roughly in the same direction as the orbital angular momentum, in the opposite direction, or somewhere in between. If the spin directions are tilted, they can cause the orbital plane to precess. Instead of the binary remaining neatly oriented in one fixed plane, the plane itself slowly changes direction. That movement can modulate the gravitational wave signal. The waveform becomes more complicated. Imagine watching a lighthouse whose entire rotating platform is also slowly wobbling. The beam would still sweep past you regularly, but its pattern would change because several motions are happening at once. Gravitational wave analysts use those distortions to infer how the black holes may have been spinning. The trouble is that different physical effects can sometimes produce similar changes. Eccentricity can alter a waveform. Precession can alter it. The orientation of the binary relative to Earth changes what we see. The ratio of the two masses matters. Individual spin magnitudes matter. Distance matters. Even gravitational lensing under the right circumstances can modify how a distant event appears. That is why having a long inspiral is so valuable. Many cycles give the analysis time to separate effects that might look similar during only one brief moment. Eventually, however, the inspiral reaches a point where the black holes are so close that the gradual approximations used to describe earlier stages become less effective. The velocities are enormous. The gravitational fields are extreme. Spacetime is being distorted so strongly that the two-object description itself begins approaching its limit. This is where the merger begins. There is no single, perfectly obvious instant at which one can say that two black holes have touched in the ordinary sense. Again, black holes do not possess solid surfaces. The defining feature is the event horizon, the boundary beyond which signals cannot escape to the outside universe. As the binary reaches its final stage, the geometry changes rapidly, and a common horizon forms around what had previously been two separate black holes. Now there is one black hole. The merger itself is astonishingly brief. For stellar mass systems, the most violent part can unfold in milliseconds. The amount of energy involved is enormous, but the process is controlled by gravity rather than by ordinary contact between pieces of matter. There are no rocks smashing, no stellar crust cracking, no molten material spraying from the point of impact. Two regions of curved spacetime become one much larger region of curved spacetime. Describing this accurately became one of the great computational challenges in relativity. Einstein wrote down the field equations of general relativity in 1915, but solving those equations for two black holes through their final orbits and merger is extremely difficult. The equations are non-linear. Everything influences everything else. The geometry determines how matter and energy move, while matter and energy determine the geometry. Even in a vacuum containing only black holes, the space-time geometry itself evolves in a complicated way. For decades, researchers could calculate the earlier inspiral using approximation techniques and understand the final settled black hole analytically, but the actual merger remained difficult to simulate. Eventually, numerical relativity made it possible to solve Einstein's equations on powerful computers and follow binary black holes through the late inspiral, merger, and ring down. Modern gravitational wave models combine analytical approximations with numerical relativity results to produce complete waveforms that can be compared with detector data. These model waveforms are essential because LIGO does not simply look at its data and wait for something obvious to appear. The instruments are constantly exposed to noise. Earthquakes happen. Wind moves buildings. Equipment vibrates. Electrical systems misbehave. Tiny environmental disturbances can enter the data. There are enough ordinary sources of trouble that running a gravitational wave observatory occasionally seems like trying to hear a pin drop while someone renovates the kitchen next door. Researchers therefore compare the detector data with expected gravitational wave patterns. One major technique is matched filtering. Very simply, the analysis asks whether the data contain a signal shaped like one of the waveforms predicted for a binary merger. Different templates represent different combinations of masses, spins, and other properties. When a strong match appears consistently across detectors, scientists can investigate whether it is likely to be astrophysical. This is one reason the full inspiral merger ring-down model matters so much. The entire waveform acts like a fingerprint. Not a perfectly unique fingerprint in every case, but a detailed one. After the two black holes merge, the story is still not finished. The new black hole is initially distorted. It has just formed from an extremely asymmetric, rapidly changing system. The remnant does not immediately become the smooth, steady object described by the familiar rotating black hole solution known as the Kerr solution. Instead, it settles. This final stage is the ring down. The distorted black hole emits gravitational waves at a set of characteristic frequencies while its deformation fades away. Physicists call these oscillations quasi-normal modes. They are determined primarily by the mass and spin of the final black hole. That is an extraordinary prediction. A newly formed black hole may have arrived through a complicated history involving two separate objects, spins pointing in strange directions and a violent nonlinear merger. But after the dust, or rather the complete absence of ordinary dust, settles, the final object's ringing can be described mainly by a remarkably small set of properties. This simplicity is related to what is often loosely called the no-hair idea. Astrophysical black holes in general relativity are expected to settle into states characterized by a small number of observable parameters, principally mass, angular momentum, and electric charge. For astrophysical black holes, charge is generally expected to be negligible, so mass and spin dominate. The ring down therefore offers a powerful consistency check. Researchers can use the inspiral to estimate the properties of the two original black holes. General relativity then predicts what sort of final black hole their merger should create. Separately, scientists can study the merger and ring down to estimate the remnant's mass and spin. If the two answers agree, general relativity passes another test. That kind of inspiral versus post-inspiral consistency test has been applied to observed black hole mergers, and the results have remained compatible with general relativity. This makes the three-stage pattern especially useful. Inspiral tells us about the approach, merger tells us about the most violent transition, ring down tells us about the object left behind. When all three are observed clearly, they reinforce one another. Suppose the inspiral indicates two black holes of particular masses and spins. The merger happens. The ring down then indicates a final black hole exactly where general relativity predicts it should be. That is a much stronger story than seeing only a brief pulse and trying to infer the entire history from the ending. GW 150914 provided a particularly clear early example. Its signal matched the general relativistic prediction across inspiral, merger, and ring down, and its frequency rose rapidly as the black holes approached one another. The LIGO analysis found that the waveform was consistent with two black holes, each around several tens of solar masses merging into one larger remnant. That is roughly what we would like every black hole merger to provide. A clean approach, a rising chirp, a strong merger, a recognizable ring down, enough cycles that researchers can watch the system change. Of course, nature is not obligated to design signals for the convenience of data analysts. Some binaries are distant, some are weak, some contain highly unequal masses, some may have strongly tilted spins, some may retain eccentricity, some merge in frequency ranges where the detectors are less sensitive, and very massive systems can appear mainly as merger and ring-down signals. That last category brings us directly back toward GW190521. Imagine two black holes much heavier than the components of GW150914. Their orbital timescales are longer, their characteristic frequencies are lower. By the time their gravitational waves rise into LIGO and Virgo's useful observing range, the binary may already be very near merger. Instead of receiving a long sequence of increasingly rapid waves, the detector receives only a handful of cycles, then the system merges, then it rings down. That is not the same as saying the inspiral never occurred. The inspiral happened. Gravity did not forget the opening act. The detectors simply may not have been sensitive to most of it. This point matters because phrases such as missing inspiral can easily sound more mysterious than the underlying physics. Suppose someone plays a piano in the apartment below yours. The lowest notes are too quiet for you to hear through the floor. Then the pianist moves higher up the keyboard and suddenly the sound becomes audible. You did not witness a piano piece that began halfway through. The earlier notes existed. Your environment filtered them out. Ground-based gravitational wave detectors also have a frequency-dependent sensitivity. Very low frequencies are difficult because slow environmental and instrumental disturbances become hard to separate from gravitational waves. At high frequencies, other noise sources become important. There is therefore a broad frequency range in which the instruments perform best, rather than perfect sensitivity to every possible gravitational wave frequency. For lower mass binaries, a substantial inspiral can pass through this region. For very massive binaries, much less does. The consequence is not merely a shorter recording, it affects what we can learn. Imagine trying to determine the speed of a car. If you watch it travel along an entire road, you can measure its motion repeatedly. If you see it only as it passes one window, the estimate becomes less precise. Now imagine you're also trying to determine whether the driver changed lanes, whether the road curved, whether the tyres slipped, and whether the car had previously stopped for petrol. One window is going to make your evening difficult. GW190521 was something like that. Its short signal contained enough information for the standard binary black hole interpretation to work, but it offered fewer opportunities to test that interpretation internally. This is also why scientists pay close attention to the ring-down. The ring-down is one of the last parts likely to remain visible in a very massive merger. If unusual compact objects or unusual spacetime structures exist, their strongest differences from ordinary black holes might appear after the merger. For an ordinary black hole, the expected behavior is comparatively straightforward. The remnant rings, the oscillations decay, energy escapes as gravitational radiation or disappears through the horizon. The signal fades. Nothing is expected to bounce repeatedly from some hard surface just outside the horizon, because an ordinary black hole has no such surface. Nothing should return from behind the event horizon. Nothing should pass through the black hole and emerge somewhere else in our universe. And certainly nothing in the standard model requires the gravitational wave to have arrived from another universe. This gives theorists a baseline. If you propose an exotic object, you need to explain how its waveform differs from that baseline. Perhaps there is an additional delayed pulse. Perhaps the ring-down frequencies shift. Perhaps part of the radiation is reflected. Perhaps a structure near where the horizon would normally be traps gravitational waves temporarily and releases them later. These hypothetical secondary features are often broadly discussed as gravitational wave echoes, although different models can produce very different kinds of echoes. An ordinary merger does not need them. That distinction becomes extremely important once wormholes enter the discussion. A wormhole capable of interacting with gravitational waves would change the boundary conditions of the problem. Instead of space-time ending, For observational purposes, at an ordinary black hole horizon, the geometry could connect to another region. Radiation might have somewhere else to go. Depending on the specific model, part of a disturbance could travel through the connection and later appear as a signal somewhere that an ordinary black hole model would not predict. But before assigning that possibility to GW190521, we have to keep comparing it against the much simpler picture. Two black holes orbit. They radiate energy, their orbit shrinks, the frequency rises, the amplitude increases, they enter the strong gravity regime, they merge, a common horizon forms, the final black hole rings, the ringing fades. That sequence is not a guess invented after gravitational waves were discovered. It follows from general relativity, and numerical simulations of binary black holes produce waveforms that match observed events with impressive accuracy. GW150914 famously followed the predicted inspiral merger ringdown pattern, and later detections have allowed increasingly detailed tests of those same strong gravity predictions. There is therefore no need to invoke anything exotic simply because black holes merge. General relativity already handles the process remarkably well. The interesting question is what happens when the detector sees only the final portion. With GW190521, the total inferred mass pushed much of the inspiral toward frequencies below the detector's strongest observing range. The result was a short signal dominated by the most violent stages. That makes the event entirely compatible with a massive black hole merger, but it also removes some of the information that would normally lock down the source history. And this is where the wording becomes important. The strange feature is not that two black holes should have produced an inspiral, and somehow failed to do so. They should have inspiraled. Under the standard explanation they did. The strange feature from our observational point of view is that we did not obtain the long, unmistakable inspiral that would have allowed us to watch the system approach its final collision. We heard the ending. We inferred the beginning. For most events, that distinction may not create much trouble. For GW190521, where the masses were already unusual and several waveform interpretations could compete within a very short data segment, it became much more important. And once you have a real signal in which the detector receives a powerful merger-like disturbance without a long visible approach, a rather unconventional question becomes possible. Could there be some physical scenario in which the missing inspiral was not merely below our observing band? Could the inspiral have happened somewhere we could not see at all? Could the violent final disturbance have reached us by a different route? The unusual thing about GW190521 was not simply that it was short. We have already seen why a very massive black hole system can naturally produce a short signal in a ground-based detector. The real difficulty was that the signal gave scientists very little of the part they normally use to reconstruct what happened before the collision. There was no long, unmistakable rising chirp sitting comfortably in the detector data. Instead, GW190521 appeared mainly as a brief burst around the merger and ringdown. LIGO and Virgo described it as a short-duration gravitational-wave signal, and later studies have continued to characterize it as unusually merger-dominated. Under the standard interpretation, this is consistent with an extremely massive binary, whose earlier inspiral occurred mostly at frequencies below the useful observing band of the detectors. So there is an important difference between saying, the inspiral did not happen, and saying, we did not clearly observe the inspiral. Those are not the same statement. The ordinary black hole merger model says the inspiral happened exactly as general relativity predicts. Two black holes orbited one another, radiated gravitational waves, lost energy, moved closer together, and eventually merged. The problem is that Earth joined the conversation very late. Imagine receiving a telephone call where the first thing you hear is somebody shouting, and that's why the table is broken, followed by a loud crash and then silence. You would have evidence that something happened. You might even reconstruct the basic event rather well. But there would be several unanswered questions about the table. With GW190521, Those unanswered questions mattered because scientists wanted to infer a surprisingly large number of properties from a surprisingly small piece of waveform. They wanted the masses, they wanted the spins, they wanted the orbital geometry, they wanted the orientation of the system, they wanted its distance, they wanted to know whether the orbit was nearly circular, they wanted to know whether the orbital plane was precessing, and ideally they would have liked nature to provide more than a fraction of a second in which to work all of this out. Nature declined. The original LIGO Virgo analysis found that if GW190521 was produced by a quasi-circular binary in spiral, the two black holes had source frame masses of approximately 85 and 66 solar masses, with substantial uncertainties. Their merger produced a remnant of roughly 142 solar masses. The network signal-to-noise ratio was 14.7, meaning the event was clearly detectable, but a strong detection is not necessarily the same thing as a richly detailed signal. That distinction is easy to overlook. You can hear a door slam very clearly without knowing who closed it. GW190521 was loud enough to be taken seriously, yet brief enough that determining the exact source configuration became unusually dependent on waveform modelling. For along in spiral, researchers get many repeated gravitational wave cycles. Those cycles help narrow down the parameters of the system because changing one property does not merely alter one moment of the signal, it affects the way the waveform develops over time. Change the masses and the chirp evolves differently. Change the spins and the phase changes. Tilt the spins and precession can create characteristic modulations. Introduce eccentricity, and the orbital motion can leave another pattern. Watch enough cycles, and these competing effects have a better chance of revealing themselves. GW19052. One did not provide much time for that separation to happen. This creates something physicists call degeneracy. The word sounds rather judgmental, but in data analysis it simply means that different combinations of physical parameters can produce signals that look similar enough that the available observations cannot easily distinguish between them. Suppose you see a shadow moving behind a curtain. It might be a dog. It might be a small person crawling around for reasons best known to them. It might be a surprisingly ambitious vacuum cleaner. If the curtain remains closed for 10 minutes, you can watch how the shadow behaves and probably settle the matter. If you see it for 1/10 of a second, your list of possibilities remains longer. GW190521 had this sort of problem. A short waveform gives different physical models more opportunity to resemble one another. That became apparent almost immediately when researchers began exploring alternatives to a simple quasi-circular binary. One possibility involved precession. If the spins of the black holes were tilted relative to the orbital angular momentum, their orbital plane could have changed orientation during the merger. The original collaboration analysis found indications that precession might have been present, although the short duration made the details difficult to determine securely. Another possibility was eccentricity. A binary that has been orbiting in isolation for a very long time is expected to lose eccentricity as it radiates gravitational waves. Its orbit becomes increasingly circular before merger, but black holes living in a crowded environment do not necessarily get such a peaceful relationship. Inside a dense star cluster, for example, black holes can have close gravitational encounters. One black hole can interact with a binary. Partners can be exchanged. Orbits can be disturbed. Two objects might become bound and merge before gravitational radiation has enough time to smooth their orbit into a nearly perfect circle. The result could be an eccentric merger. Several analyses have investigated this possibility for GW190521. One numerical relativity study found that, within the set of simulations considered, the event was most consistent with a highly eccentric merger, while other work showed that eccentricity and spin-induced precession could imitate one another well enough that the data did not allow a confident distinction. That is already a warning against treating one unusual waveform feature as a unique signature of exotic physics. If two ordinary black hole configurations can imitate each other, imagine how careful we have to be before adding something as dramatic as a wormhole. There was also the possibility of an almost head-on encounter. Instead of two black holes spending a long time in a graceful inward spiral, perhaps they approached one another on an extremely eccentric trajectory and collided after relatively little orbital motion. Numerical work has shown that signals from highly eccentric or head-on, intermediate mass black hole encounters can sometimes be confused with signals from precessing quasi-circular binaries at the signal strengths available to current detectors. GW190521 was specifically discussed as an event for which this degeneracy could matter. A head-on collision would certainly help explain why someone looking for a beautiful, extended inspiral might be disappointed. There simply would not be much of one. That does not mean the head-on explanation has replaced the standard binary model. It has not. These configurations are expected to require particular formation circumstances, and comparing them properly requires waveform models capable of describing the relevant dynamics. But the exercise demonstrates why GW190521 became such an interesting laboratory. The data were good enough to tell us that a powerful relativistic event had occurred. They were not good enough to force every reasonable physical model into one narrow interpretation. The short duration also made the exact beginning of the merger difficult to define observationally. For a long signal, analysts can choose an early section of inspiral and follow the system through time. With GW190521, much of what lies inside the detector band is already strong field physics. Researchers are examining the black holes when they are very close together, moving rapidly and strongly distorting spacetime. This is exactly the regime in which general relativity is most interesting. It is also one of the least forgiving places to have limited information. Think of watching two cars from a helicopter. If you see them driving along separate roads for 20 minutes before they meet at an intersection, you know quite a lot about where they came from. If the camera turns on half a second before impact, reconstructing their previous routes becomes considerably harder. The crash itself may be perfectly visible, the history is not. GW190521 therefore contains an odd combination of certainty and uncertainty. We are highly confident that the detectors saw a gravitational wave event. The standard black hole merger model provides a good explanation. The data are consistent with general relativity. At the same time, some details of the source remain much less secure than they would be for a long inspiral. That combination is precisely what attracts theoretical physicists. If a signal fits only one model beautifully, and every alternative performs terribly, there is not much room for speculation. If a signal is mostly noise, speculation is not especially useful either. But a real, statistically significant event with an unusual waveform and several plausible interpretations is much more inviting. You can use it to test ideas, not because those ideas are likely to be correct, but because the data give them something concrete to confront. There is another reason the missing inspiral matters. The inspiral normally establishes continuity. You see the system approaching the merger. You see the frequency increasing. You see the amplitude changing. Then you see the collision. The stages connect naturally. With GW190521, that continuity is weaker from the observational point of view. Much of the detected signal can be described using the merger and ring down alone. A 2023 analysis, for example, described GW190521 as a short duration, low frequency signal consistent with the ring down and possibly some of the inspiral merger of an intermediate mass black hole coalescence. That study found ring-down models with multiple quasi-normal modes that could be made consistent with broader inspiral merger ring-down analyses. That matters because the ring-down has a different relationship with the source history. The inspiral tells us about two black holes. The ring-down mostly tells us about one. Once the merger has happened, the newly formed remnant begins settling toward the stable rotating black hole geometry predicted by general relativity. Its ringing carries information about the mass and spin of the final object, but much of the detailed history of how that object formed has already been compressed into a much smaller set of observable properties. This creates a peculiar situation. Suppose you detect a strong ring down. You may infer that a black hole-like object is settling. But if you did not clearly observe the approach, the ring down alone gives you less direct information about where the original objects were before the final event. That possibility becomes important once we begin thinking about gravitational wave echoes. An echo, in the broadest sense used in this area of research, is an additional gravitational wave feature arriving after, or separate from, a main disturbance because some unusual structure has delayed, reflected, trapped, or transmitted part of the radiation. Different models predict different echo patterns. Some involve exotic compact objects. Some modify the region near where an event horizon would normally be. Some involve speculative quantum effects. And the proposal relevant to GW 190521 takes the idea in a much more dramatic direction. Instead of asking whether an ordinary merger happened here and produced an unusual late-time signal, it asks whether the merger happened somewhere else entirely. That possibility was developed explicitly in a study published in 2026 examining whether GW 190521 could be interpreted as a single gravitational wave echo pulse associated with a wormhole remnant. The authors focused partly on exactly the feature we have been discussing. GW 190521's extremely short duration and the absence of a clearly identifiable inspiral phase in the observed data. Their proposed scenario starts by moving the ordinary black hole merger away from us, very far away in a rather unusual sense. Imagine a region of space-time that cannot normally send light or gravitational waves directly into our observable universe. In the most extreme version, it may belong to another universe. Two black holes merge there. They produce the normal violent disturbance. A remnant forms. But the geometry of that remnant is not an ordinary black hole. Instead, it contains or becomes connected to a wormhole whose throat links that region to ours. Part of the post-merger gravitational radiation travels through that connection. It emerges on our side. Our detector sees the pulse. But we never see the inspiral because the original binary was never visible from our region in the first place. That is a completely different explanation for the same observational fact. In the standard picture, the inspiral existed in our universe, but most of it was at frequencies LIGO and Virgo could not observe well. In the wormhole picture, the inspiral happened somewhere our detectors had no direct access to, while a later piece of the disturbance reached us through the wormhole. Same broad observation, very different geometry. And this is why the absence of a clear inspiral becomes interesting rather than merely inconvenient. If GW 190521 had contained a long, beautifully measured inspiral followed continuously by the merger and ring down, a proposal in which the detected pulse had simply emerged through a wormhole from another universe would face a much more obvious problem. We would already have watched the binary here. There would be little reason to move the source somewhere else. But when the observation is dominated by a short final pulse, the origin of that pulse becomes more open to testing. Notice the word testing, not believing. The distinction is essential. The wormhole interpretation does not become likely merely because it can be imagined. The researchers proposing the model had to calculate the sort of gravitational wave signal their wormhole scenario could produce, and compare that signal directly with GW 190521. Their model produced a network signal-to-noise ratio comparable to the standard binary black hole fit. However, when they performed Bayesian model selection, the result favoured the conventional binary black hole explanation, with a reported log Bayes factor of about -2.9 for the wormhole echo model relative to the BBH model. In plain language, the ordinary black hole merger still fit the data better. That is an important result even if you are hoping for a doorway to another universe. The wormhole model did not win. The conventional explanation remains preferred. But the speculative model was not simply a sentence followed by several question marks. It produced a waveform. It was compared with real detector data. And that changes the status of the discussion from pure imagination to a concrete testable proposal. There is still an enormous gap between A model can reproduce aspects of this signal, and we have detected a wormhole. A model can fit data for the wrong reason. Different models can fit short signals similarly. The assumptions behind the wormhole itself may be physically difficult to realize. Future data may favor the ordinary interpretation much more strongly. Another analysis with improved waveforms may alter the comparison. Science contains many ideas that survive an initial comparison with data and then quietly disappear when better measurements arrive. This is normal. In fact, it is healthy. A good speculative hypothesis should make itself vulnerable. It should tell you what observations would make it look worse. Otherwise, it is not doing much scientific work. GW190521 is particularly useful because future gravitational wave detections can provide additional cases. One strange short signal is difficult to interpret. A population is different. Suppose detectors eventually observe many extremely massive mergers with very short waveforms. If all of them can be described naturally by ordinary black hole populations, eccentric encounters, precession, hierarchical mergers, and detector selection effects, the motivation for exotic alternatives becomes weaker. If some events repeatedly show additional structures that ordinary black holes cannot reproduce, interest in more unusual explanations increases. Patterns matter. One event can surprise you. 20 events can tell you whether the surprise has rules. The detectors themselves are also improving. Better low-frequency sensitivity would be particularly valuable because it could allow researchers to observe more of the inspiral from high-mass binaries. That would remove some of the ambiguity that made GW190521 so difficult. If a future GW190521-like event is observed with a clear inspiral before the merger, many alternative explanations would become easier to test. If instead a strong isolated merger-like or echo-like pulse appears with no compatible preceding inspiral, even when the detectors should have been able to see one, that would be considerably more interesting. This is how an odd event becomes a prototype for future tests. GW19052. One does not need to be a wormhole for it to help us search for wormholes. That may be the most useful way to think about it. Scientists do not have to decide that the exotic explanation is true before asking what it would look like. They can take the theoretical model, generate its predicted signal, compare it with existing observations, and then prepare to test it against better observations later. The shortness of GW190521 makes this possible because its origin is not documented by a long visible approach. We have a gravitational disturbance, we have a probable explanation, and we have enough uncertainty in the details to ask whether a completely different space-time geometry could imitate part of the same event. It is also useful to remember that unusual signals have a habit of becoming less unusual as astronomy improves. The first example of almost anything looks peculiar. The first pulsars were so regular that researchers briefly considered whether an artificial source needed to be taken seriously. The first quasars looked unlike ordinary nearby stars despite appearing point-like in early observations. Gravitational wave astronomy itself is still young compared with optical astronomy. LIGO's first direct detection arrived only in 2015. GW190521 appeared less than 4 years later. We are listening to a part of the universe that humanity has only recently learned how to hear. It would be surprising if every signal immediately fitted into a perfectly tidy category. GW190521 may ultimately turn out to be an especially massive but entirely conventional black hole merger, with some combination of unusual formation history, spin, eccentricity, or observational limitations. That remains the sensible baseline. Yet the very fact that we can use the data to constrain stranger possibilities is new. A century ago, wormholes were not even part of the discussion. A few decades ago, gravitational waves had still not been directly detected. Now researchers can take a mathematical model involving a wormhole throat, calculate how a gravitational disturbance might behave around it, and ask whether a real signal recorded by instruments in Washington, Louisiana, and Italy resembles the prediction. That is a remarkable change in what counts as testable physics. And it leads us to the next problem. So far, we've been using the word wormhole as though everyone has agreed on what one actually is. They have not. Before we can ask whether GW 190521 might have arrived through a wormhole, we need to be clear about what physicists mean by a wormhole in the first place. The word has become so familiar through films, novels and television that it's easy to picture a glowing circular doorway floating in space, ready to deliver a spacecraft to another galaxy before anyone has finished making the tea. General relativity is considerably less convenient. At its simplest, a wormhole is a possible geometry of space-time in which two regions are connected through a route that does not exist in ordinary flat space. The important word there is geometry. A wormhole is not necessarily a tunnel drilled through some material that fills the universe. It is a feature of space-time itself. This distinction comes directly from Einstein's general theory of relativity. In Newtonian physics, we can imagine space as a fixed arena where objects move and gravity acts between them. General relativity changes that picture. Matter and energy influence the geometry of space-time, and objects move according to that geometry. A planet orbiting a star is not simply being pulled across a rigid background. It is following a path through curved space-time. Black holes are an extreme example of the same idea. Once space-time becomes something that can possess geometry, rather than merely providing a stage, unusual geometries become mathematically possible. One of them is a connection between regions that would otherwise seem separate. The standard illustration uses a sheet of paper. Draw 2 points far apart on the sheet. If you have to travel along the surface, getting from one point to the other requires crossing the distance between them. Fold the paper so the 2 points come close together, then imagine making a short tunnel from one side to the other. The path through that tunnel could be much shorter. The illustration is useful provided we do not take it too literally. The sheet represents ordinary space only by pretending that space can be bent into another surrounding dimension that we can see from outside. A real wormhole does not necessarily require our three-dimensional space to be physically folded like a piece of office stationery inside some accessible fourth spatial dimension. The diagram is a way of representing intrinsic curvature, not a photograph of what space-time would look like from a convenient viewing platform. There probably is not a cosmic employee standing outside the universe folding it carefully along a dotted line. The mathematics does not need one. A more useful way to picture a traversable wormhole is to imagine two entrances, usually called mouths, connected by a throat. From outside, the mouths could be very far apart through ordinary space. They might sit on opposite sides of a galaxy, or much farther apart than that. Yet the proper distance through the throat could be relatively short. Suppose one mouth were near Earth, and the other were near a star 10,000 light-years away. Without a wormhole, even a light beam needs 10,000 years to cross the ordinary distance between us and that star. If the wormhole's internal route were only a few kilometers long, a traveller entering one mouth could, in principle, cross that short route and leave through the other. The traveller has not locally exceeded the speed of light. They have simply taken a shorter path. That is the key point behind the phrase shortcut through space-time. General relativity does not allow an ordinary object to accelerate through its local surroundings past the speed of light. A wormhole does not have to violate that local rule. Instead, it changes which locations are close to one another. A similar idea appears whenever geometry gives us routes that differ from what an external picture suggests. Imagine an ant walking across a large curved surface. Two places that seem widely separated in one representation may be connected differently when the full geometry is taken into account. The ant does not need to break its speed limit. The shape of its world determines the available route. Wormholes take that basic geometric idea somewhere much more extreme. There is another detail that science fiction sometimes slides past rather quickly. A wormhole does not necessarily have to connect two distant locations in the same universe. Some solutions and extensions of general relativistic spacetimes contain multiple asymptotic regions. From the perspective of observers living in them, those regions can behave rather like separate universes. A bridge in the geometry can mathematically connect them, even though an ordinary traveller could not simply cross from one to the other. Einstein and Nathan Rosen's famous 1935 work described a geometry involving two identical sheets joined by a bridge, although their purpose was not to design an interstellar transport system. They were investigating whether particles might be represented without the singularities that appeared in the gravitational description available to them. This is important for our GW190521 story. When physicists talk about a wormhole connecting another universe to ours, they do not necessarily mean a parallel universe in the popular sense, where another version of you is currently having a slightly more successful afternoon. They may mean another region of the full spacetime geometry that is not ordinarily connected to our observable region by causal paths accessible to us. That sounds like a small distinction, but it changes the physics considerably. The word universe can be used rather loosely in these discussions. What matters mathematically is how the spacetime regions are connected, and whether light, matter, or gravitational disturbances can travel between them. A wormhole also should not automatically be confused with a black hole. The two can look related because the history of wormhole physics is deeply connected with black hole solutions, but their useful properties are very different. An ordinary astrophysical black hole has an event horizon. Cross it, and the causal structure of space-time prevents you from sending a signal back outside. You're not passing through a convenient hallway. You're entering a region from which future-directed paths do not lead back to the exterior. A traversable wormhole, by definition, must allow something to pass from one side to the other and emerge. That means its geometry cannot simply trap every traveller behind an ordinary event horizon before they reach the other mouth. If you enter a supposed shortcut and the only available destination is the singularity, travel brochures should probably mention that fairly prominently. Physicists therefore distinguish between wormhole-like geometries that are traversable and those that are not. That distinction is central. The Einstein-Rosen bridge associated with the maximally extended Schwarzschild geometry is not the straightforward traversable tunnel imagined in most science fiction. In the standard description, the bridge pinches off too quickly for a traveller or light signal to move through it from one external region to the other. The geometry contains the connection mathematically, but it does not provide a usable passage. A traversable wormhole requires something more carefully arranged. In the late 1980s, Michael Morris, Kip Thorne, and later Ulvi Yurtsever studied wormhole geometries specifically from the perspective of whether a traveller could actually cross them. Their work helped establish the modern discussion of macroscopic traversable wormholes, and showed that keeping such a structure open raises serious questions about the energy conditions normally obeyed by familiar forms of matter. For now, we can leave the strange matter problem waiting politely outside. It will not remain there for long. What matters here is what a successful traversable geometry would need to do. A traveller approaching the first mouth should not encounter an event horizon that permanently traps them. They should not be torn apart by intolerably large tidal forces if the wormhole is meant for human travel. The throat should stay open long enough to cross, and the geometry should connect to an exit rather than quietly ending somewhere inconvenient. That list sounds perfectly reasonable until you ask Einstein's equations to provide it. Then the invoice arrives. One useful feature of wormhole models is that the distance between the mouths measured through ordinary external space and the distance through the throat do not have to agree. This gives us the shortcut. Suppose the mouths begin close together. In a hypothetical construction, one mouth might then be moved very far away through ordinary space, while the internal connection remains much shorter. Someone using normal space must cross the long external distance. Someone using the wormhole takes the short internal route. Nothing about the local motion through the throat requires them to move faster than light. Yet from the perspective of someone who stayed outside, the traveller may appear to have reached the distant location far sooner than a light beam sent through ordinary space could have done. This is one reason wormholes are often described as enabling effective faster-than-light travel. The phrase needs care. Locally, the traveller remains slower than light. Globally, the geometry gives them a shortcut. And once general relativity allows shortcuts of that kind, another problem appears almost immediately. Time. If the two mouths experience different motions or different gravitational environments, relativity can make their clocks accumulate different amounts of elapsed time. Under suitable hypothetical conditions, moving between the mouths could then connect not only distant places but differently timed events. Morris, Thorne, and Yurtsever showed in 1988 that if a traversable wormhole could be created and maintained, it could in principle be manipulated into a configuration containing closed time-like curves, effectively turning it into a type of time machine. They also emphasise that whether such wormholes can physically be created and maintained depends on unresolved issues involving quantum field theory and gravity. This is one of those moments when theoretical physics takes something already difficult and decides it has been behaving far too sensibly. We began with a shortcut. A few calculations later, causality itself is asking to speak with the management. Fortunately, we do not need time machines for the GW190521 idea. The relevant possibility is simpler. Could a wormhole connect one region of spacetime with another and allow a gravitational disturbance to pass through? Gravitational waves respond to spacetime geometry. If a wormhole is genuinely traversable for the relevant perturbations, then the boundary conditions around the wormhole differ from those around an ordinary black hole. For a normal black hole, gravitational radiation approaching the horizon can cross inward and cannot later emerge from that horizon into the same exterior region. For a wormhole, there may be another side. Radiation entering the throat might propagate into the connected spacetime. Likewise, disturbances produced near the other mouth could potentially influence what happens on our side, depending on the specific geometry. Researchers have examined theoretical ways in which objects or fields on one side of a traversable wormhole could produce observable effects on the other side. One study showed that a wormhole connecting two spacetimes could allow gravitational influence from matter near one mouth to affect orbital motion near the other, illustrating that the connection would not necessarily be hidden from external observation. That begins to show why wormholes can be discussed observationally, rather than merely as mathematical curiosities. If a wormhole existed, it should interact with its surroundings. Light could be bent by its geometry, matter could orbit it. A wormhole might create lensing patterns, its gravitational field could affect nearby stars. And if a violent event happened in or near the connected region, gravitational waves might carry information about the geometry. Researchers have therefore studied potential electromagnetic and gravitational signatures that could distinguish wormholes from black holes, although no macroscopic wormhole has been observationally established. These proposals remain theoretical tests of hypothetical geometries rather than detections. There is a useful change in attitude here. For many years, the most common wormhole question was, could we travel through one? That is understandable. Humans discover a hypothetical structure in the equations connecting distant parts of the universe, and our first instinct is apparently to ask whether there is room for luggage. But from the scientific point of view, a better first question is often, what would one do to the things around it? You do not need to enter an object to discover it. Nobody has entered a neutron star. Nobody has placed a measuring instrument just above the event horizon of a distant black hole. Astronomy works by observing effects. We detect stars through their light. We infer planets through their influence on stars. We identify black holes from radiation produced by surrounding matter, stellar orbits, gravitational lensing, and gravitational waves. A wormhole search would follow the same general logic. Find a prediction that differs from ordinary astrophysical objects, then look for it. The difficulty is that wormholes can imitate black holes surprisingly well. From a large distance, a compact wormhole with sufficient mass could bend light and influence orbits in ways that resemble an ordinary black hole. Some theoretical models are deliberately constructed as black hole mimickers. Recent calculations continue to explore cases where orbital properties outside a wormhole can closely reproduce those around a Kerr black hole, while differences appear only closer to the throat or in other observables. This means that simply seeing something dark and massive is not enough. Even producing an image that resembles a black hole shadow would not necessarily settle the question by itself. You would need to look for detailed differences. The same principle applies to gravitational waves. Suppose two ordinary black holes merge. General relativity predicts the inspiral, merger, and ring down. Now suppose the final compact object has a wormhole-like structure instead. The late-time behaviour may differ. Radiation that would have disappeared through an event horizon might interact with the throat. Some modes could be transmitted. Some could be reflected by an effective potential around the object. Signals could be delayed. The precise result depends heavily on the chosen wormhole model, which is why physicists cannot simply say, "A wormhole makes echoes," and consider the problem solved. You first have to specify the geometry. How wide is the throat? What holds it open? What spacetime lies on the other side? How does the gravitational perturbation propagate through the connection? What boundary conditions apply? Does the structure remain stable after being disturbed? Only then can you calculate a waveform. This is particularly relevant to the claim involving GW 190521. The idea is not that any mysterious gravitational wave pulse can be declared a wormhole signal whenever its shape looks inconvenient. The proposed wormhole interpretation depends on building a specific space-time model and calculating how a disturbance associated with a black hole merger might emerge through it. That is a much higher standard. It also explains why the discussion immediately runs into questions about stability. A wormhole that exists for an infinitesimal moment and collapses before anything can cross is not very helpful for transmitting a gravitational wave pulse from one region to another. A useful wormhole needs a throat that remains open under the conditions relevant to the signal, and general relativity does not make that easy. Consider what gravity normally does to matter. Put enough positive mass and energy in a compact region, and gravity pulls inward. Make the region sufficiently compact and a black hole can form. A traversable wormhole requires a throat that does something almost opposite to what naive gravitational intuition expects. Instead of collapsing shut, it must flare outward and remain open. The geometry needs support. In the familiar Morris-Thorne class of traversable wormholes, this requirement is linked to violations of standard energy conditions. Later studies have produced many variants and attempted to reduce, redistribute, or reinterpret the required exotic stress energy. But the issue has never simply vanished. This is one reason we have to be careful with the statement that general relativity allows wormholes. Mathematics can admit a geometry without guaranteeing that nature contains the material or physical process needed to create it. Einstein's equations also allow many idealized situations that may never be realized astrophysically. The important question is not only whether we can write down a metric, it is whether the full system is physically consistent. Can the wormhole form? Can it remain stable? Does the necessary stress energy exist? Do quantum effects destroy it? Would matter passing through destabilize it? Would the throat collapse under the very gravitational wave we hope to transmit? Those questions are much harder than drawing two circles connected by a tube. Even apparently promising traversable solutions face substantial constraints. For example, work in semi-classical gravity has argued that standard static, spherically symmetric traversable wormhole geometries cannot arise as physically accessible limits of corresponding dynamical semi-classical solutions, illustrating how seriously quantum restrictions may constrain the classical wormhole picture. That does not prove every imaginable wormhole is impossible. Different theories of gravity, quantum effects, higher dimensional models, and specialized constructions continue to be studied. It does tell us that Einstein's equations contain a wormhole solution is only the beginning of the conversation. The existence of a map does not guarantee the road has been built. There is another reason wormholes remain scientifically valuable, even if macroscopic traversable examples never exist. They expose the limits of our theories. A wormhole forces general relativity to confront quantum field theory. It forces physicists to ask what sorts of negative energy are permitted. It raises questions about causality. It probes the relationship between geometry and information. And, as we will eventually see, modern work on quantum gravity has produced situations where wormhole geometry appears in connection with quantum entanglement in ways that Einstein and Rosen could hardly have anticipated. So the wormhole is useful even before we find one. It is a stress test for physics. Ask whether a spacetime can contain a shortcut, and suddenly you need to understand gravity, quantum fields, horizons, topology, energy conditions, information and causality. It is rather like asking whether you can add a small extension to the kitchen and discovering that the builder would first like to discuss the foundations of reality. For GW 1905-21, however, we need one particular version of the idea. Imagine that somewhere inaccessible to us directly, two black holes merge. Their inspiral and collision generate gravitational waves. Normally those waves propagate outward through the space-time containing the source. But suppose the post-merger geometry includes a wormhole connection. One mouth lies in the source region, the other opens into ours. A portion of the gravitational disturbance enters the throat. It travels through the connection and reaches our side. From our perspective, we do not observe the long inspiral because it happened in the other region. We receive only the part capable of propagating through the wormhole. A short gravitational wave signal suddenly appears in our detectors. That is the conceptual route from wormhole geometry to the proposed interpretation of GW 1905-21. It sounds exotic because it is exotic. The ordinary black hole merger explanation requires none of this, and it still fits the event better. But now the alternative has a clear physical question behind it. Could a space-time bridge actually remain open long enough to transmit such a disturbance? The first famous bridge between different regions of space-time did not begin as a proposal for interstellar travel. Albert Einstein and Nathan Rosen were not sitting in Princeton in 1935 trying to work out how quickly someone could get to another galaxy without missing dinner. They were dealing with a different problem. General relativity had already produced solutions containing singularities, places where quantities in the mathematics could become infinite, or where the usual description of space-time appeared to break down. Einstein was deeply uncomfortable with the idea that fundamental particles should simply be represented by singular points. He and Rosen wondered whether matter might instead be described entirely through smooth gravitational and electromagnetic fields. Their paper was called The Particle Problem in the General Theory of Relativity, and their goal was to investigate whether a particle could be represented without introducing a singularity into the field equations. In the process, they described a geometry made from two identical sheets of space joined by what they called a bridge. That bridge would later acquire a much more glamorous reputation. Today we call it an Einstein-Rosen bridge, and if you have encountered the phrase mainly through science fiction, you may reasonably assume that Einstein and Rosen had discovered a tunnel through which one could travel. Unfortunately for anyone already packing a suitcase, that is not what the original construction gives us. To see why, we need to return to the geometry around a simple non-rotating black hole. The exterior gravitational field of such an object can be described by the Schwarzschild solution to Einstein's equations. From far away, the geometry behaves exactly as we expect for a spherical mass. Move closer, however, and something interesting happens at a particular radius. This is the Schwarzschild radius. For an ordinary black hole, that radius marks the event horizon. From the outside, the horizon is not a physical wall. You would not crash into it. There is no solid shell waiting there, and there is no sign saying, "Black hole begins here. Please keep arms inside the spacecraft." Instead, it is a boundary in the causal structure of space-time. Once something crosses it, every physically allowed path into that object's future leads farther inward. Light cannot escape back to the external universe. matter cannot turn around and climb out. The problem is not that the black hole has an unusually powerful suction system. The geometry itself has been arranged so that outward escape is no longer among the available future directions. The familiar Schwarzschild coordinates make the event horizon look mathematically troublesome. But that particular trouble turns out to be largely a coordinate problem, rather than a physical singularity at the horizon itself. With better coordinates, the spacetime can be extended smoothly across that location. And when physicists perform the full mathematical extension of the idealized Schwarzschild solution, they find more spacetime than the simple exterior picture suggests. There is one external region. There can also be another external region. Between them lies the bridge-like geometry associated with the black hole. On a carefully chosen spatial slice, the two exterior regions look as though they are connected by a throat. This is where the famous image comes from. Two large regions, a narrow connection, a geometric neck between them. It certainly looks like a wormhole. The problem appears when you ask whether anything can actually use it. A photograph of a bridge is not much good if the bridge vanishes every time a car approaches. The Einstein-Rosen connection in the eternal Schwarzschild geometry is non-traversable. The two exterior regions belong to the full mathematical extension, but no ordinary observer can enter one external region, pass through the bridge, and emerge in the other. The causal structure does not permit that journey. Modern discussions of Einstein-Rosen bridges therefore distinguish them sharply from the traversable wormholes considered later. One way of understanding the problem is to think about how the bridge changes with time. The familiar diagram showing a smooth throat connecting two sheets is a snapshot of the geometry at a particular instant. It does not tell you what the bridge is doing before or after that instant. That is rather important. A photograph of a closing elevator door can look like a perfectly good opening if you do not know which way the doors are moving. For the Einstein-Rosen bridge, the throat does not sit there indefinitely waiting for travellers. The geometry evolves in such a way that the passage closes before a signal can cross from one exterior region to the other. If you try to enter, you do not emerge through the second mouth. The routes available to you carry you toward the black hole interior instead. So when people say that the Einstein-Rosen bridge pinches off, they do not mean that there is necessarily a rubbery tunnel floating somewhere and physically squeezing itself shut like the neck of a balloon. They mean that the space-time geometry does not maintain a causal path connecting the two exteriors for long enough to permit passage. That sounds like a technical distinction, but it is the entire difference between an interesting diagram and a usable wormhole. Suppose you stand beside one mouth and shine a flashlight into it. For a traversable wormhole, you would want that light to travel through the throat and emerge from the other mouth. For an Einstein-Rosen bridge associated with the ordinary eternal Schwarzschild solution, that does not happen. The light does not complete the journey, neither would you. This means the original bridge is not a shortcut in the practical sense. It is a connection in the mathematical structure of the space-time, but not a corridor through which information can travel from one exterior region to the other. That makes it useful for understanding black hole geometry, and much later, for thinking about quantum gravity and entanglement. It makes it less useful for getting to Alpha Centauri. There is another subtlety. Real astrophysical black holes are not expected to form as eternal Schwarzschild black holes that have existed forever, with two perfectly symmetric external regions already attached. Real black holes form when matter collapses. A massive star exhausts its fuel. Its core collapses. Under appropriate conditions, an event horizon forms. The resulting spacetime does not simply reproduce every region of the maximally extended eternal solution in the same physical way. This is one reason the phrase "there is a wormhole inside every black hole" is far too simple. The mathematical extension of an idealized eternal black hole contains an Einstein-Rosen bridge. That does not mean the black holes formed from collapsing stars around us contain open passages leading conveniently to other universes. If they did, astronomy would have become considerably more awkward. The distinction also helps explain why the word wormhole covers several related but very different ideas. An Einstein-Rosen bridge can refer to the non-traversable connection associated with a black hole geometry. A Morris-Thorne wormhole, by contrast, is constructed specifically to be traversable. Other models arise in modified theories of gravity, higher dimensional spacetimes, semi-classical gravity, or quantum gravity settings. Some connect distant places in one universe. Some connect separate asymptotic regions. Some exist only briefly. Some are static in the idealized mathematics. Some possess horizons. Some are designed specifically not to. Simply asking, do wormholes exist? Is therefore a little like asking, do vehicles exist? Before deciding whether you mean bicycles, submarines, or airport baggage carts. The details matter. For tonight's question, the most important detail is traversability. If gravitational radiation from some inaccessible region is going to reach us through a wormhole, then the relevant disturbance needs a path through the geometry. A bridge that cannot transmit signals will not help. That is why the work of Michael Morris and Kip Thorne in the 1980s became so important. Instead of beginning with a known black hole solution and discovering a bridge inside its mathematical extension, they reversed the problem. They asked what sort of geometry a wormhole would need if a human traveller were actually meant to pass through it. That sounds almost like an engineering exercise. There should be two mouths. There should be a throat joining them. There should be no event horizon blocking the traveller. The journey should take a finite amount of time. Tidal forces should ideally remain survivable. And the throat should not close before the traveller reaches the other side. The famous 1988 work by Morris and Thorne developed precisely this type of traversable wormhole as a tool for thinking through general relativity. Related work by Morris, Thorne, and Ulvi Yurtsever then examined what would follow if such a wormhole could be created and maintained, including the possibility that suitable motion of its mouths could turn it into a time machine. They stressed that the real difficulty lay in whether the laws of physics permit such wormholes to be produced and kept open at all. Keeping it open is where the trouble begins. Gravity normally encourages collapse. If you put enough positive mass and energy into a sufficiently small region, you do not naturally get a pleasant tunnel held open for visitors. You move in the direction of stronger curvature and, under the right conditions, black hole formation. A traversable wormhole asks the geometry to do something different. Near the throat, the geometry needs to flare outward. You can picture a narrow region reaching a minimum size, and then opening back out toward the other side instead of continuing to collapse inward. For this to happen in the simplest general relativistic wormhole models, the stress and energy around the throat must behave in ways that ordinary matter does not normally behave. This becomes clearer if we return to a simple thought experiment. Imagine constructing a tunnel with a circular throat. If the geometry around that throat were supported only by ordinary positive energy matter, gravity would tend to pull the structure inward. Add more ordinary mass to strengthen it, and you may actually make the gravitational collapse problem worse. The support you need is not quite like adding stronger steel beams to a bridge. The space-time requires an unusual pattern of energy, density, and pressure. In many classic traversable wormhole models, this means violating what physicists call an energy condition. Energy conditions are sets of assumptions about how physically reasonable matter should behave. They are not separate forces of nature. They are mathematical restrictions placed on the stress-energy tensor, the object in general relativity that describes the density and flow of energy and momentum. One of the most relevant is the null energy condition. Very loosely, it says that an observer moving along a light-like direction should not measure the particular combination of energy, density, and pressure required to become negative. Ordinary classical matter tends to satisfy this condition. A Morris-Thorne-style traversable wormhole generally does not. The throat needs what became known as exotic matter. Matt Visser later showed ways to design traversable wormholes in which the amount or placement of this exotic material could be reduced, but the example still violated the weak energy condition. The word exotic can make this sound more mysterious than it is. It does not automatically mean a new glowing substance stored in a container marked "Do Not Shake." It means matter or energy with stress energy properties outside the familiar classical conditions normally assumed in general relativity. Quantum field theory complicates the story because quantum fields can produce local negative energy densities in certain circumstances. That means nature does not enforce the classical energy conditions absolutely in every possible situation. This sounds promising for wormholes. Then physics takes the promise back almost immediately. Negative quantum energy is constrained. You cannot simply request an unlimited amount, arrange it however you like, and keep it there for as long as necessary. Quantum energy inequalities place restrictions on the magnitude and duration of negative energy in many settings. Modern work continues to examine whether quantum fields can produce the stress energy needed for traversable wormholes, and how restrictive those conditions are. A 2022 analysis, for example, argued that standard static, spherically symmetric traversable wormholes cannot arise as accessible limits of dynamical semi-classical solutions of the type studied there, while a 2026 calculation found specific parameter regions in which a quantized massive scalar field can satisfy Morris-Thorne support conditions for a particular zero tidal force wormhole model. These results illustrate that the question remains highly model-dependent rather than settled by one simple statement that quantum negative energy either saves or kills all wormholes. There is also a more practical stability problem. Suppose somehow you produce exactly the stress energy needed to hold the wormhole open. Now send something through it. That object has mass. It carries energy. Its presence changes the space-time geometry. The wormhole must respond. A tunnel that is stable only when absolutely nothing enters it is not much of a transport system. It is more like a museum exhibit with unusually strict rules. A gravitational wave creates a similar conceptual issue. Gravitational waves carry energy and perturb the geometry. If we want a wormhole to transmit a signal like the one proposed in the GW 190521 scenario, the throat has to survive the disturbance well enough for the relevant wave to propagate through it. That requires studying dynamical stability rather than merely drawing a static solution. A metric can look perfectly respectable while nobody touches it. The harder question is what happens after it is disturbed. Does the throat oscillate and settle? Does it grow? Does it collapse into a black hole? Does the supporting stress energy respond in a physically consistent way? Does the disturbance itself destroy the structure that was supposed to carry it? These are exactly the kinds of questions that separate a mathematical wormhole solution from a believable astrophysical object. There is a useful analogy with balancing a pencil on its tip. There is nothing mathematically impossible about a pencil standing perfectly upright. If you specify its position exactly and assume no disturbances, there it is. The difficulty arrives when the table vibrates, the air moves, or somebody nearby becomes curious. A physically useful configuration must survive small disturbances. Wormhole stability can be much more complicated than the pencil problem, but the principle is similar. Writing down a solution is not enough. You have to ask whether nature can keep it there. This is also why the original Einstein-Rosen bridge is such an instructive starting point. It demonstrates that spacetime geometry can contain something that looks remarkably like a connection between separate regions, but it also demonstrates that connection does not imply traversability. The bridge exists in the mathematical structure, yet its causal behaviour prevents an ordinary crossing. Morris and Thorne then showed what properties a genuinely traversable geometry would need, and once those requirements are imposed, the problem moves from geometry into matter. What holds the throat open? Einstein's equations connect the geometry of spacetime on one side of the equation with matter and energy on the other. You cannot freely choose an attractive wormhole shape and then leave the stress energy blank. If you demand the geometry, the equations tell you what kind of material source would be required. Sometimes the answer is something ordinary. For a star, it might be a fluid with positive density and pressure. For the classic traversable wormhole, the answer becomes much stranger. This does not necessarily mean all possible wormholes are ruled out. Researchers have explored rotating wormholes, dynamical wormholes, thin shell constructions, modified gravity, higher dimensional models, quantum effects, and other ways of changing the problem. But every successful model has to pay its bill somewhere. Perhaps the bill is exotic stress energy. Perhaps it is an altered gravitational theory. Perhaps it is a restricted geometry. Perhaps it is an instability. Perhaps it is a wormhole so tiny that sending a spacecraft through it is no longer an especially urgent question. And occasionally the bill arrives in the form of causality. If a traversable wormhole connects two mouths, and those mouths experience different amounts of elapsed time, relativity can create a time shift between them. Morris, Thorne and Yurtsever showed that under hypothetical conditions, a maintained traversable wormhole could be converted into a system containing closed time-like curves, allowing a traveller to return to an earlier event. They presented this not as a practical construction plan, but as evidence that wormholes raise deep questions about quantum gravity, energy conditions, and whether nature protects causality. For our purposes, we can leave the time machine switched off. A wormhole transmitting gravitational radiation does not need to send the wave into its own past. It merely needs to remain traversable long enough for information to cross from one region to another. Even that smaller request is demanding. The throat cannot behave like the original Einstein-Rosen bridge and close before the signal gets through. It cannot hide the exit permanently behind an event horizon. It cannot become catastrophically unstable under a small perturbation. And whatever supports it must be allowed, at least in principle, by the deeper laws of physics. This brings us to a slightly awkward situation. General relativity gives us the idea. General relativity also tells us why the easiest version fails. The Einstein-Rosen bridge connects regions but is not traversable. A traversable modification can be written down, but in the classic construction it requires unusual stress energy. Quantum theory allows some negative energy behavior but also places restrictions on how that behavior can occur. So the question changes. We are no longer asking whether spacetime can be drawn with a throat. It can. What would have to exist around that throat to keep gravity from closing it? Geometry alone is no longer enough. Einstein's equations require us to explain what kind of matter or energy produces that geometry. And for the simplest traversable wormholes, the answer is something ordinary matter does not seem willing to provide. Physicists usually call it exotic matter. That name is slightly unfortunate because it immediately suggests an undiscovered substance with a strange colour, an unpleasant smell, and a storage container somewhere beneath a secret laboratory. That is not really what exotic matter means here. It does not refer to one specific particle waiting to be discovered. It refers to matter or quantum fields whose distribution of energy and pressure behaves in an unusual way, particularly by violating certain assumptions known as energy conditions. To understand why a wormhole might need this, imagine the throat again. The geometry narrows toward a minimum radius, and then opens outward into another region of space-time. If the throat is going to remain traversable, it must resist collapsing under gravity. Ordinary positive mass tends to make gravity attractive. Pack enough ordinary matter into a compact region, and space-time curves inward more strongly. A traversable wormhole requires something different near its throat. The geometry has to flare outward, rather than simply continuing toward gravitational collapse. When Morris and Thorne worked out their famous traversable wormhole models, they found that this flaring out condition demanded unusual stress energy near the throat. In the standard Einstein theory, the required material violates what is called the null energy condition. That basic difficulty has remained central to wormhole physics ever since. The null energy condition sounds more complicated than it needs to for our purposes. General relativity does not describe matter simply by writing down how many kilograms are sitting in a particular place. Matter is represented by something called the stress-energy tensor. It keeps track not only of energy density but also pressure, momentum, and stresses. That is important because pressure itself contributes to gravity in general relativity. The null energy condition places a restriction on combinations of those quantities when measured along the paths that light can follow. For familiar classical forms of matter, the condition is usually satisfied. A traversable wormhole throat in the classic construction needs it violated. In practical terms, the geometry demands a region where the relationship between energy density and pressure becomes unusual enough to produce the outward flaring structure. One way this can happen is through negative energy density. Negative energy is another phrase that invites misunderstanding. It does not mean that you can place -5 kilograms on a bathroom scale, nor does it mean that a negative energy object necessarily flies upward while everything else falls downward. It is a property of the energy associated with a field relative to an appropriate reference state. And before we go any farther, we should clear one popular candidate from the room. Antimatter is not the exotic matter required to hold open a wormhole. Antimatter has positive inertial mass. It contains positive energy. An antiproton is not a proton with negative mass. A positron is not an electron that has somehow misplaced its gravity. In 2023, the Alpha collaboration directly observed the gravitational behavior of antihydrogen and found that it falls toward Earth, with the measurements consistent with ordinary attractive gravity and strongly excluding a simple repulsive one-gravity scenario. So filling a wormhole with antimatter would not solve the problem. It might create several new problems involving the unfortunate tendency of antimatter to annihilate when it meets matter, but holding open spacetime would not automatically be one of the benefits. Dark matter does not provide an obvious solution either. The name dark occasionally makes it sound mysterious enough to qualify for every unexplained job in cosmology, but dark matter is invoked because of its gravitational influence and lack of ordinary electromagnetic emission, not because it possesses the negative energy properties required by the classic traversable wormhole throat. What wormhole physicists need is stranger than simply an unfamiliar particle. They need the stress energy itself to behave in a particular way. At first, this might seem to finish the story. Ordinary matter has positive energy. A traversable wormhole needs negative energy. Therefore, wormholes cannot exist. But quantum field theory makes that conclusion too quick. In quantum physics, the vacuum is not quite the completely empty nothing that everyday intuition suggests. Quantum fields remain present even when there are no ordinary particles around. Their states can fluctuate, and under certain arrangements, the renormalized energy density in a region can be lower than the energy density assigned to the ordinary vacuum state. This allows negative energy densities to appear in a meaningful quantum field theory sense. So negative energy is not merely something physicists invented because a wormhole calculation demanded it. Quantum theory already contains situations in which it occurs. Studies of quantum fields have long established that local energy densities can become negative, while later work has explored how such negative regions are constrained. The most famous example usually brought into the conversation is the Casimir effect. Imagine two conducting plates positioned extremely close together in a vacuum. The presence of the plates changes the allowed modes of the quantum electromagnetic field between them compared with the modes outside. The result is a measurable force between the plates. In an idealized description, the renormalized vacuum energy density between the plates can be negative relative to the vacuum outside. This is not imaginary mathematics. The Casimir effect is a genuine quantum phenomenon. But it is very important not to jump from that statement to, excellent, we have wormhole fuel. A real Casimir apparatus includes the plates, whatever structure holds them apart, and all of the positive energy contained in that equipment. A 2022 analysis specifically examined whether the negative Casimir energy could make the mass of a complete apparatus negative. Under physically reasonable equilibrium conditions, the researchers showed that when the supporting material obeys the dominant energy condition, the total mass remains positive. So we cannot simply build a large collection of Casimir plates, pour the negative energy into a tank, and drive it over to the nearest wormhole. Negative energy does not behave like petrol. Quantum field theory allows it, but quantum field theory is also rather possessive about the conditions under which it appears. This leads to one of the biggest obstacles in the entire subject. Negative energy seems to be restricted in both magnitude and duration. Physicists studying this problem developed what are known as quantum inequalities, or more generally, quantum energy inequalities. These place bounds on how much negative energy an observer can encounter when the energy density is averaged over some interval of time. The rough lesson is that nature appears reluctant to let you have a large amount of negative energy for a long time. You may be allowed something strongly negative for a very short interval, or something mildly negative for longer. But an enormous stable reservoir of negative energy sitting calmly in the laboratory is another matter. Ford and Rosen studied these restrictions in detail during the 1990s. Their work showed that quantum field theory bounds can place severe constraints on traversable wormholes supported by negative energy. In one influential analysis, they concluded that either the wormhole would have to be only slightly larger than the Planck scale, or the geometry would require extreme differences between its characteristic length scales, with negative energy concentrated in extraordinarily thin regions. The Planck scale is not remotely close to the sort of wormhole entrance into which you might fly a spacecraft. The Planck length is around 10 to the power of minus 35 meters. A proton is enormous by comparison. If your interstellar transportation system requires passengers to become vastly smaller than a proton before boarding, the passenger experience has room for improvement. The other option is not especially comfortable either. Perhaps the wormhole throat is macroscopic, but the negative energy region has to be confined to an incredibly thin layer compared with the size of the throat. That creates demanding conditions on the geometry and on whatever quantum fields are supposed to support it. Researchers have tried to design wormholes that minimize the total amount of exotic matter. This is a perfectly sensible strategy. If nature gives you an ingredient only reluctantly, use as little of it as possible. Some models appear to allow arbitrarily small total quantities of exotic matter while maintaining a macroscopic throat. But when quantum inequalities were applied more carefully, strong restrictions returned. Fuster and Rosen found that examples of this type could be forced into submicroscopic dimensions or into geometries with extreme differences in length scale. One model they examined became effectively non-traversable because reaching the throat would take an infinite amount of the relevant trajectory parameter. The universe, it seems, has read the small print. There is another complication hidden inside the phrase negative energy. A negative region rarely gets to exist without consequences elsewhere. Quantum field theory often connects negative energy pulses with compensating positive energy. Some results suggest a kind of quantum bookkeeping in which producing a negative energy region requires positive energy to appear in ways that prevent unlimited exploitation of the effect. You cannot necessarily take the helpful negative part and leave the bill somewhere else indefinitely. This does not amount to a single, universal rule covering every quantum field in every curved spacetime, but it captures an important theme in the research. Negative energy is physically allowed, yet strongly constrained, and that creates a fascinating tension. Classical general relativity tells us what sort of stress energy can support a traversable wormhole. Quantum field theory tells us that stress energy with some of those strange properties can exist. Then quantum field theory immediately places restrictions on how much of it you can have, and for how long. It is like being told that the impossible ingredient in a recipe does technically exist, but you may borrow 1 grain for 3/billionths of a second and must return it immediately. This is why the phrase wormholes require exotic matter should not be translated into either extreme conclusion. It does not mean that physicists have discovered a practical substance capable of holding wormholes open. They have not. But it also does not mean that the required violation is obviously forbidden by every known law of physics. Quantum fields can violate the classical energy conditions. The real question is whether they can do so in precisely the amounts, shapes, durations, and gravitational environments needed for a useful wormhole. That question is still active. In fact, it became more interesting very recently. A study published in July 2026 calculated the renormalized stress-energy tensor of a massive scalar quantum field in a particular zero-tidal force wormhole geometry. The authors found regions of their model's parameter space in which the quantum field satisfied the Morris-Thorne conditions needed to support that specific wormhole configuration, along with other parameter regions where it could not. This does not establish that macroscopic wormholes exist, but it shows how current research is moving beyond simply assuming an unspecified blob of exotic matter, and instead asking whether concrete quantum fields can produce the required stress energy self-consistently. That is an important shift. Early discussions could write down a wormhole geometry, examine Einstein's equations, notice that strange matter was required, and then label the strange part exotic. Modern semi-classical calculations can ask a harder question. Choose an actual quantum field, place it in the wormhole spacetime, calculate its vacuum stress energy, then check whether that stress energy is capable of supporting the geometry that you assumed. Ideally, the two sides of the problem should agree. This is called back reaction. Matter determines spacetime, but spacetime also affects the quantum fields living within it. If you calculate one while pretending the other never responds, you may miss the most important part of the physics. A stable wormhole should therefore be a self-consistent solution, rather than a geometric shape supported by an unexplained negative energy placeholder. This is where the subject becomes extremely difficult. We do not yet possess a complete experimentally confirmed theory of quantum gravity. General relativity works extraordinarily well for large-scale gravity. Quantum theory works extraordinarily well for particles and fields. A wormhole forces us into a situation where both may matter at once. If the throat depends on quantum negative energy to prevent gravitational collapse, then treating gravity as entirely classical, while treating matter quantum mechanically, may only be an approximation. Eventually, the geometry itself may need a quantum description. And once that happens, our familiar picture of exotic matter holding open a pre-existing tunnel may no longer be the best way to think about the problem. There are also attempts to avoid exotic matter by changing the gravitational theory itself. In modified theories of gravity, terms beyond Einstein's original equations can sometimes contribute effectively to the wormhole supporting geometry. Then the ordinary matter may obey familiar energy conditions, while the additional gravitational terms provide the behavior that, in standard general relativity, would have been attributed to exotic matter. That does not automatically make such wormholes physically real. It moves the uncertainty. Now we must ask whether the modified theory is correct, whether it agrees with existing gravitational tests, whether the wormhole is stable, and whether the required parameters can occur in nature. There are very few free lunches in fundamental physics. Occasionally, there is a lunch where the bill has simply been moved to another table. For the GW 1905-21 proposal, however, we do not need to solve every engineering problem associated with a human-sized wormhole. The question is narrower. Could a wormhole-like spacetime exist long enough and with the right causal structure to transmit a gravitational disturbance? A gravitational wave does not need a cabin. It does not need oxygen. It does not care about tidal forces in the way a human body does. So some restrictions that matter enormously for a spacecraft are less relevant to a wave, but the central stability requirement remains. The throat must stay sufficiently open, the perturbation must have a causal path through it, and the stress energy supporting the geometry must survive the interaction, rather than collapsing the entire structure into an ordinary black hole. That brings us back to a feature we have seen repeatedly. A wormhole may be easier to draw than to maintain. The Einstein-Rosen bridge gives us a connection that cannot be crossed. The Morris-Thorne construction gives us a traversable geometry, but demands unusual stress energy. Quantum field theory gives us negative energy, but limits its availability. Modified gravity can rearrange the requirements but introduces new assumptions. Every route seems to remove one obstacle and reveal another one standing immediately behind it. Yet something unexpected happened. when physicists stopped thinking about wormholes purely as classical tunnels and began studying black holes through quantum information. The question gradually changed from, what strange substance can hold this throat open, to something much deeper. The strange matter needed to hold open a classical wormhole brings us to a point where general relativity can no longer comfortably handle the problem on its own. The geometry is gravitational, but the ingredient that might prevent the throat from collapsing appears to depend on quantum physics. And once quantum theory enters the discussion, the wormhole story changes in a way that nobody examining Einstein's equations in the 1930s could have anticipated. The change begins with entanglement. Quantum entanglement is one of those ideas that sounds mysterious even after someone explains it correctly, which is probably why it has accumulated so many misleading explanations over the years. Two quantum systems can become entangled when their properties are described by a shared quantum state, rather than two completely independent states. Suppose we prepare two particles in a particular entangled state, and then separate them. One particle goes to one laboratory. The other travels to another laboratory very far away. When researchers perform suitable measurements on the particles, the results show correlations stronger than would be possible for a broad class of theories in which the particles merely carried predetermined local instructions from the moment they separated. Modern Bell tests have repeatedly observed correlations consistent with quantum mechanics and incompatible with local hidden variable explanations of the relevant kind. None of this means that one particle sends an ordinary message to the other when it is measured. That point is worth keeping nearby because entanglement is frequently introduced with phrases such as instant communication, which create more trouble than they solve. Imagine Alice has one entangled particle and Bob has the other. Alice makes a measurement. Her result is unpredictable. Bob measures his particle. His result is also locally unpredictable. When Alice and Bob later compare their records through an ordinary communication channel, they discover the quantum correlations. But Alice cannot choose her result and use it to transmit a controllable message to Bob faster than light. So if Alice wants to send Bob the extremely urgent information that she has run out of biscuits, she still needs an ordinary signal. Entanglement will not rescue tea. The idea was already troubling physicists in 1935. That year, Albert Einstein, Boris Podolsky, and Nathan Rosen published the famous EPR paper questioning whether quantum mechanics provided a complete description of physical reality. Their argument focused on quantum correlations between separated systems and the apparent tension between those correlations and a classical idea of independently existing local properties. You may notice a familiar name, Rosen. The same Nathan Rosen who worked with Einstein on the bridge we discussed earlier, and the timing is rather remarkable. In 1935, Einstein and Rosen published their work on what became known as the Einstein-Rosen bridge. Also in 1935, Einstein, Podolsky and Rosen published the EPR argument concerning quantum correlations. For decades, these looked like separate subjects. One concerned the geometry of spacetime, the other concerned the foundations of quantum mechanics. One produced the initials ER, the other produced EPR. There was no obvious reason to put an equal sign between them. Then black holes complicated everything. Black holes create an uncomfortable meeting place for general relativity and quantum mechanics, because they possess extraordinarily strong gravitational fields while also raising fundamental questions about quantum information. General relativity tells us what the geometry around a black hole should look like. Quantum theory tells us that information behaves according to quantum rules. When researchers try to understand what happens to quantum information in black hole evaporation, these two extremely successful theories begin making demands that are difficult to satisfy simultaneously. This became the black hole information problem. We do not need every detail of that problem tonight, but one part matters enormously for ER equals EPR. Quantum entanglement is central to the way physicists describe black holes. In particular, theorists studying certain idealized black holes discovered that a spacetime containing two exterior regions connected by a non-traversable Einstein-Rosen bridge can be described using two quantum systems in a highly entangled state. Juan Maldacena developed an influential version of this connection in 2001 while studying eternal black holes in anti-de Sitter space, usually shortened to ADS. In the holographic description he considered, the two exterior regions correspond to two copies of a quantum field theory prepared in a specific entangled state. Anti-de Sitter space is not a direct description of the large-scale universe we live in. It is a space-time with a different cosmological geometry. Physicists study it because it offers unusually powerful mathematical tools for investigating quantum gravity. In particular, the ADS/CFT correspondence connects certain gravitational theories in an ADS space-time with quantum theories defined on its boundary. This gives researchers two descriptions of the same underlying physics. One description speaks the language of gravity and geometry. The other speaks the language of quantum fields and entanglement. That is exactly the kind of situation in which something surprising can happen. On the gravity side, you may see a wormhole. On the quantum side, you may see entanglement. At first, this connection applied to a particularly organized situation involving eternal black holes and specially entangled quantum states. Then, in 2013, Juan Maldacena and Leonard Susskind proposed taking the relationship much more seriously. Their paper was titled Cool Horizons for Entangled Black Holes. The basic conjecture became known as ER equals EPR. Maldacena and Susskind suggested that the Einstein-Rosen bridges connecting certain black holes and the Einstein-Podolsky-Rosen entanglement between quantum systems might represent two aspects of a deeper underlying relationship. They began with maximally entangled black holes and suggested that similar bridge-like connections could be associated more generally with entangled states. That is an enormous idea packed into 6 characters. ER equals EPR. But we have to be careful about what the equal sign means. It does not mean that two entangled electrons sitting on opposite sides of a laboratory contain a normal little cylindrical tunnel between them. There is no microscopic doorway that a third electron can casually wander through. There is certainly no reason to imagine tiny astronauts waving at one another through quantum wormholes. The conjecture is about a possible deep relationship between quantum entanglement and spacetime connectivity. In certain gravitational systems, what appears as entanglement in one mathematical description can correspond to connected geometry in another. The surprising possibility is that spacetime may not be something that simply exists first, with quantum particles placed inside it afterward. Some aspects of spacetime geometry might emerge from patterns of quantum entanglement. That turns our earlier wormhole question upside down. Previously, we imagined spacetime as a flexible geometric object. We bent it. We connected two regions. Then we asked what matter could support the connection. ER equals EPR suggests that this may not be the deepest description available. Perhaps the connection itself is related to the entanglement structure of the quantum state. In that case, asking what a wormhole is becomes partly a question about quantum information. Consider two black holes that are extremely strongly entangled. In the gravitational description, an Einstein-Rosen bridge may connect their interiors, yet the bridge is still non-traversable. Alice cannot jump into one black hole and emerge safely from the other. A light beam cannot simply cross from one exterior region to the other. This is important because ordinary quantum entanglement cannot be used to send faster-than-light messages either. The non-traversability of the bridge fits rather neatly with the no-communication property of entanglement. The geometry is connected. The quantum systems are correlated. But neither description gives Alice a convenient instantaneous telephone line. That parallel was one of the reasons the idea attracted so much attention. It hints that rules which appear to be about quantum information may have geometric counterparts. A restriction on communication in the quantum description may appear as a non-traversable wormhole in the gravitational description. A change to the quantum interaction may alter the geometry. And this is where the idea begins reconnecting with the exotic matter we just discussed. For several years after ER equals EPR was proposed, the wormholes in the best understood examples remained non-traversable. There could be a bridge, but nothing could cross it from one boundary to the other. Then Pingao, Daniel Jafferis and Aaron Wall found a remarkable theoretical result. They studied an eternal black hole geometry in anti-de Sitter space with two boundaries. By introducing a particular interaction coupling the quantum theories associated with those two boundaries, they found that the resulting quantum stress energy could produce negative average null energy. The gravitational back reaction of that negative energy changed the geometry enough to make the Einstein-Rosen bridge traversable. Notice what has just returned: negative energy. We spent the previous part watching negative energy cause trouble for classical traversable wormholes. Now it appears again, but in a much more controlled quantum gravitational setting. The wormhole begins non-traversable. A carefully specified quantum interaction changes the stress energy. That stress energy modifies the space-time. The modification allows a signal to pass through. The result does not provide a recipe for building a doorway in your garage. The setting involves an idealized ADS space-time and a very specific holographic construction, but conceptually it was a major development. Traversability was no longer merely imposed by writing down exotic matter and asking it to hold the throat open. Here, the negative energy emerged from a defined quantum interaction in a theory where the gravitational and quantum descriptions could be related precisely. And there was another surprise. Gao, Jafferis and Wall pointed out that the traversable wormhole process had a close relationship to quantum teleportation. Quantum teleportation also suffers from a slightly over-enthusiastic name. It does not make an object disappear from one laboratory and reappear in another. Instead, it allows an unknown quantum state to be transferred using shared entanglement plus ordinary classical communication. The original physical particle does not fly through space to the receiver. The quantum information describing its state is reconstructed elsewhere through a protocol involving entanglement and the transmission of classical information. Under the ER equals EPR viewpoint, something fascinating can happen in holographic models. The quantum description may look like a teleportation protocol. The gravitational description may look like information traveling through a traversable wormhole. These are not necessarily two separate events. They can be two descriptions of the same process. From one perspective, quantum information is teleported. From another, a signal crosses a wormhole. If that sounds as though physics has begun translating between two completely different languages, that is essentially what holographic duality allows theorists to do. One language speaks of quantum degrees of freedom, interactions and entanglement. The other speaks of geometry, horizons and wormholes. A difficult calculation in one language can sometimes become an intuitive geometric statement in the other. This is one reason ER equals EPR is more profound than simply saying entanglement makes wormholes. The conjecture suggests that geometry and entanglement may be linked so deeply that what we call spatial connectivity could depend on the pattern of quantum relationships underneath it. Imagine gradually reducing the entanglement between two parts of a holographic quantum system. In some theoretical settings, the geometric connection between the corresponding regions becomes weaker. Increase the appropriate entanglement, and the connected geometry can become more substantial. This has contributed to a broader research program investigating whether space-time itself emerges from quantum information. If that idea is correct in some sufficiently general sense, then distance may not be fundamental in quite the way we normally imagine. Two regions could be geometrically related because of the structure of entanglement in an underlying quantum state. Again, this does not mean that every entangled pair gives us a shortcut we can travel through. The distinction between geometric connection and traversable passage remains essential. Two rooms can share a wall without having a door. ER equals EPR may give you the wall. Traversability requires considerably more paperwork. There is another reason the conjecture became important. It offered a new way to think about the black hole information problem. One of the tensions in black hole physics concerns how quantum entanglement is distributed between a black hole, the radiation it emits, and the degrees of freedom near its horizon. In 2012, the so-called firewall argument sharpened that tension dramatically. Maldacena and Susskind developed ER EPR partly in response to those issues, proposing that entanglement involving black holes might be represented through highly quantum Einstein-Rosen bridges, rather than requiring the conventional picture to fail in the most violent possible way. We do not need to solve the firewall debate here. The useful point is that wormholes were becoming something very different from hypothetical tubes for transportation. They became part of a conversation about how quantum information is stored, shared, and represented by spacetime itself. That development changes how we should think about the phrase real wormhole. A real wormhole does not necessarily have to resemble the large, stable tunnel of a science fiction film. At the quantum gravity level, wormhole geometry might describe relationships between systems in ways that have no simple classical picture. Some wormholes may be non-traversable, some may be tiny, some may exist only in highly idealized theoretical settings, some may represent quantum connections more naturally than transportation routes, and some carefully engineered theoretical models can become traversable without allowing any violation of ordinary causality. Gao, Jaffrus and Wall explicitly found that their traversable construction could not be used to violate causality, despite allowing passage through the bridge. That last detail matters. Whenever physicists produce a wormhole that allows information to cross, one of the first questions is whether they have accidentally built a faster-than-light messaging system or a time machine. In this case, the surrounding quantum description keeps the process consistent with causality. The information transfer requires the interaction coupling the two sides. The wormhole does not provide a completely independent secret route that lets you ignore the causal structure of the full system. Once again, quantum information geometry seem to be enforcing the same rules in different languages. Now return for a moment to GW 190521. The proposed interpretation of that gravitational wave signal does not prove ER equals EPR. It does not require that every wormhole be produced by entanglement, and the observational wormhole model involved in the GW 190521 discussion should not simply be identified with the specific holographic ADS wormholes used in ER equals EPR research. These are different theoretical settings, but they belong to the same larger change in modern physics. Wormholes are no longer investigated only as curious classical solutions that appear when Einstein's equations are manipulated in unusual ways. They now appear in serious work connecting gravity with quantum information. Researchers can ask whether quantum effects can make certain wormholes traversable. They can ask whether entanglement corresponds to geometry. They can ask whether information that looks teleported in a quantum system looks as though it travelled through a wormhole in the gravitational description. And increasingly, they can ask whether simplified versions of these ideas can be implemented in controllable quantum systems. That final step created some rather excitable headlines. A few years ago, researchers reported experiments on quantum processors designed to reproduce dynamics related to traversable wormhole models. The phrase wormhole created in a quantum computer appeared very quickly. As you might expect, the actual result requires considerably more care. Nobody opened a portal in a laboratory, nobody sent a particle into a processor in California and watched it emerge beside Saturn. What researchers did was use quantum systems to simulate or implement mathematical dynamics that have a gravitational interpretation involving a traversable wormhole in a particular theoretical model. Whether that should be described as making a wormhole depends heavily on what one means by making, and that distinction is exactly where we are heading. Because the next question is no longer merely whether entanglement and wormholes might be related in an equation. The question is whether a wormhole-like quantum system can actually transmit information from one side to the other, whether that process can be tested in a laboratory, and what those experiments really tell us about wormholes that might exist in the universe. A non-traversable Einstein-Rosen bridge may connect two regions in the mathematical description of spacetime, but it cannot carry a usable signal from one exterior region to the other. A traversable wormhole has to do more. Something must enter one side. Information about that thing must travel through the system, and something carrying that information must become accessible on the other side. For years, this remained mostly a theoretical exercise. Then physicists discovered that a carefully arranged quantum interaction could change the situation. The basic construction comes from the work of Ping Gao, Daniel Jafferis, and Aaron Wall. They considered two entangled quantum systems with a gravitational description involving a two-sided black hole and a non-traversable Einstein-Rosen bridge. Normally, if you throw a signal into one side, it cannot cross the bridge and appear at the other exterior, but introducing a particular interaction between the two sides changes the quantum stress energy. In the gravitational description, that produces the negative energy effect needed to open a temporary causal path through the wormhole. A signal sent in at the appropriate time can then emerge from the other side. This is not the same as placing a permanent metal support inside a classical wormhole. The effect is dynamical. The wormhole starts out non-traversable. The two sides are coupled in a carefully chosen way. That coupling changes the effective geometry. For a limited interval, information can pass through. Then the opportunity closes again. If you imagine the bridge as a door, it is less like building a normal doorway and more like arranging a very precise sequence in which the door opens briefly just as your message reaches it. Miss the timing, and the message does not make the trip. This already tells us something important about the phrase stable wormhole. A wormhole does not necessarily need to remain open forever to transmit information. It only needs to remain traversable for long enough. For a person crossing a macroscopic tunnel, that might require a substantial amount of time and an extremely well-behaved geometry. For a quantum signal, the requirement can be much smaller. The message does not need a comfortable seat. It just needs a causal route. The next question is what information passing through such a wormhole would look like from the quantum side of the theory. And here the answer turns out to be closely related to quantum teleportation. Quantum teleportation does not physically transport an object from one location to another. It transfers the quantum state. Suppose Alice has a qubit containing some quantum information that she wants Bob to receive. Alice and Bob already share an entangled resource. Alice performs particular operations involving her qubit and her part of the entangled system. Classical information is communicated. Bob then performs the required operation on his side. The original unknown quantum state can be reconstructed there. Nobody has moved a physical particle through the intervening space in the ordinary sense. The state has been transferred using entanglement and communication. In the wormhole-related protocols, physicists found that this quantum information process can have another description. On one side of a holographic duality, you see a teleportation protocol occurring in an entangled many-body quantum system. On the gravitational side, the same process can be represented as a signal entering one mouth of a traversable wormhole and emerging from the other. Leonard Susskind and Ying Zhao developed this relationship explicitly, describing quantum teleportation as having a dual interpretation in which the teleported quantum information passes through an Einstein-Rosen bridge that has been made traversable by the operations required for the protocol. That does not mean the teleportation secretly uses a physical tunnel through the laboratory. The two descriptions belong to a particular theoretical correspondence. On the quantum side, there are qubits, entanglement, interactions, and information transfer. On the gravity side, there is a black hole geometry and a wormhole. If the duality is valid for the system under consideration, those can describe the same underlying dynamics in two different languages. This is difficult to picture because we are accustomed to asking which description is the real one. Did the information teleport, or did it travel through a wormhole? In a true holographic duality, that may be the wrong question. It is somewhat like asking whether a computer file is really a picture on your screen, or really a pattern of electronic states inside the machine. Those descriptions operate at different levels, but they refer to the same physical process. The analogy is imperfect, but it gets us closer. The wormhole description can make certain aspects of the information transfer geometrically intuitive. The quantum description tells us how to implement the process. This led researchers to an obvious and slightly dangerous question. If the quantum side of the wormhole process can be described as operations on entangled quantum systems, could we perform those operations on an actual quantum computer? Not simulate a spaceship, not generate an image of a wormhole, actually implement the quantum dynamics corresponding to the wormhole protocol. To understand how that became possible, we need a model called the Sachdev-Yakitaev model, usually abbreviated SYK. The full details of SYK could occupy a very long evening by themselves, and we do not need them. The useful feature is that the model describes a strongly interacting quantum many-body system with unusual chaotic behavior. In suitable limits, aspects of its low-energy physics have a gravitational description related to a nearly two-dimensional anti-de Sitter spacetime. This made SYK an important testing ground for ideas involving black holes, scrambling, holography, and traversable wormholes. Maldacena and Chi showed that two appropriately coupled SYK systems can have a description corresponding to an eternal traversable wormhole, with the necessary negative null energy generated by quantum effects associated with the coupling. We have therefore moved through several layers. Entanglement can be related to geometric connectivity. Certain entangled black hole systems correspond to non-traversable bridges. A carefully chosen interaction can make the bridge traversable. The same process has a quantum teleportation description, and models such as SYK give physicists a quantum system in which those ideas can be studied concretely. The remaining problem was hardware. The full quantum systems theorists would ideally like to study can be far too complicated for present-day quantum processors. Modern quantum computers are still noisy. They have limited numbers of high-quality qubits. Long calculations involving many quantum gates accumulate errors. So taking a large theoretical SYK model and simply telling a quantum computer to run it is not an especially productive plan. The processor may respond in the technical language of experimental physics, which is mostly noise. Researchers therefore looked for smaller versions that preserved the particular behavior they wanted to study. This led to the experiment that produced one of the more memorable science headlines of 2022. A team led by Daniel Jaffris and Maria Spiropoulou implemented traversable wormhole-related dynamics on Google's Sycamore quantum processor. The experiment used machine learning techniques to construct a much smaller, sparsified version of an SYK-like system that could fit on available quantum hardware. The implemented circuit used 9 qubits and 164 2-qubit gates. The researchers prepared 2 entangled quantum systems, inserted quantum information into one side, applied the interaction associated with making the wormhole traversable, and measured how the information appeared on the other side. Naturally, newspapers and websites had to decide what to call this. Researchers implemented a small quantum many-body teleportation protocol with a holographic gravitational interpretation is accurate enough. It is also unlikely to survive a headline meeting, so the world got variations of "Scientists created a wormhole in a quantum computer." That sentence needs several asterisks. No physical tunnel opened inside the Sycamore processor. Space-time in the laboratory was not bent into a shortcut. There were no 2 mouths sitting on opposite sides of the chip. Nothing could be sent from the quantum computer to another star. The experiment reproduced quantum dynamics that, through the theoretical holographic correspondence being studied, have a gravitational interpretation resembling information passing through a traversable wormhole. Nature's own accompanying description emphasized that the experiment simulated or realized the behavior of a wormhole in a virtual or holographic setting, rather than constructing a literal tunnel through ordinary laboratory space-time. That may sound less dramatic. Scientifically, it is still remarkable. The goal was not to build a transportation device. The goal was to ask whether a quantum processor could become a laboratory for mathematical structures associated with quantum gravity. Usually, quantum gravity is difficult to test because the relevant scales are far beyond ordinary experiments. We cannot casually manufacture black holes and place them next to detectors. We cannot visit the event horizon of Sagittarius A star with a box of instruments, and we certainly cannot order an anti-de Sitter universe for next Tuesday. Quantum simulation offers a different route. If a gravitational system is mathematically dual to a quantum system that can be controlled in the laboratory, then researchers may be able to test properties of the quantum description and study their gravitational interpretation. The 2022 Sycamore experiment looked for several specific signatures rather than simply observing that a qubit eventually appeared somewhere else. Ordinary quantum teleportation can already transfer quantum states. If that were the only thing observed, there would be little reason to invoke wormholes. The researchers therefore examined features predicted by the traversable wormhole interpretation of the model. They reported behavior associated with scrambling and thermalization, a structure called size winding, an asymmetry linked to the sign of the coupling that corresponds in the gravitational picture to a negative energy shock wave, a time delay effect analogous to gravitational propagation, and the expected causal ordering of signals emerging from the wormhole model. Size winding is particularly important in this line of work. When information enters a strongly interacting chaotic quantum system, it becomes scrambled. A simple local piece of information spreads into increasingly complicated combinations of the system's degrees of freedom. Physicists can describe this spreading using the effective size of quantum operators. In the holographic dictionary used for these models, that operator growth is related to the motion of an infalling particle in the gravitational description. Under the right conditions, the distribution of operator sizes develops a special phase structure called size winding. The interaction between the two entangled systems can then reverse or redirect the process so that the scrambled information becomes accessible on the other side. Brown and collaborators developed this idea under the name teleportation by size, arguing that the protocol can reproduce characteristic behavior associated with traversable wormholes, while also clarifying that more generic many-body systems can display related information transfer effects without possessing a clean semi-classical wormhole geometry. That final qualification is crucial. Not every successful teleportation experiment demonstrates a wormhole dual. Quantum systems can move information around in many ways. Scrambling can occur without gravity. Entanglement can exist without a simple geometric interpretation. Teleportation can be implemented without anyone mentioning Einstein. So the interesting question is not merely whether information makes it from left to right. It is whether the entire pattern of dynamics matches the special behavior expected from a quantum system with a useful gravitational dual. This became the subject of debate after the Sycamore result. In 2023, Bryce Cobrin, Thomas Schuster, and Norman Yao published a detailed criticism of the learned Hamiltonian used in the experiment. They argued that the small model did not exhibit some of the broader chaotic and thermalizing properties claimed for the full SYK system, that the strongest teleportation resemblance was associated with operators included in the machine learning procedure, and that some of the observed size-winding behavior could occur generically in small, fully commuting models rather than uniquely indicating holographic wormhole dynamics. That criticism did not mean the experiment had secretly failed to teleport quantum information. The issue was interpretation. How faithfully did the simplified model preserve the gravitational features of the larger SYK theory? Was the observed behavior genuinely diagnostic of a wormhole dual? Or had the process of compressing the model into something small enough for current hardware preserved a few desired signatures while losing too much of the underlying chaotic physics? These are serious questions because quantum simulation depends on exactly this kind of faithfulness. Suppose you construct a tiny model of a hurricane in a laboratory. If the model reproduces the rotation of the storm but does not reproduce the fluid dynamics responsible for real hurricanes, you should be careful about what you claim to have learned. Likewise, if a simplified quantum Hamiltonian reproduces teleportation signature, researchers need to know whether the result comes from the same structure that gives the larger theoretical model its gravitational interpretation. The original team defended the physical relevance of their construction, and research on holographic teleportation and SYK-like systems has continued rather than stopping with the 2022 experiment. The debate is therefore not usefully summarized as one group having created a wormhole and another group having proved they did not. The accepted point is much narrower. A small quantum processor implemented a specially designed quantum model, displaying several dynamics associated with traversable wormhole protocols, while how strongly that small learned model should be interpreted as a faithful instance of holographic gravity has been contested. There is also an important philosophical difference between simulation and duality. Suppose you simulate the solar system on a laptop. Nobody says Jupiter exists inside the laptop. The computer represents Jupiter mathematically. A holographic duality is stronger than an ordinary numerical simulation. If two theories are truly dual, they are alternative descriptions of the same physics rather than one simply approximating the other from the outside. That is why researchers sometimes use stronger language for quantum gravity experiments based on holography. But the difficulty is that the precise duality relating a particular small noisy laboratory system to a smooth gravitational spacetime may itself be approximate. The 9-qubit experiment was deliberately small. The semi-classical gravitational interpretation becomes cleaner in theoretical limits, involving much larger systems than 9 qubits. So it is safest to say that the experiment implemented wormhole-inspired or holographically motivated dynamics rather than announcing the construction of a literal wormhole. That safety does not make the work boring. Quite the opposite. The experiment took ideas developed through black hole thermodynamics, quantum information, holography, and general relativity, and compressed a controlled version of them onto real quantum hardware. Instead of merely calculating the teleportation protocol on paper, researchers could perturb a quantum system and watch the information dynamics unfold. That provides a new kind of testbed. The hardware does not reproduce the astrophysical universe. It allows researchers to investigate mathematical mechanisms that may be important in quantum gravity. The field has continued developing. In 2024, researchers studying SYK wormholes classified several symmetry classes of traversable wormhole behavior and continued exploring how the same near-conformal dynamics appear in coupled quantum systems and gravitational descriptions. Other work investigated how conserved quantum currents affect the negative energy mechanism that makes holographic wormholes traversable, and how that changes the amount of information a wormhole-like channel can transmit. By 2026, theorists had begun describing traversable wormholes explicitly as quantum communication channels. One recent preprint calculated the quantum channel capacity of the Gauge-Ferris Wall protocol, asking not merely whether 1 qubit can make it through, but how much quantum information the wormhole process can transmit. The authors connected that capacity to the growth of quantum operators and proposed it as a benchmark for future wormhole simulations. That is a surprisingly practical question for something involving wormholes. How much data can the wormhole carry? Not how many astronauts. Not whether a spaceship fits. How many qubits? In this part of modern physics, the first traveller through a wormhole is increasingly likely to be information. Another 2026 preprint reported a quantum processor implementation of a traversable wormhole-inspired teleportation protocol using a chaotic, sparse SYK model with 8 Majorana degrees of freedom. The authors specifically designed the model to preserve spectral chaos while reducing the circuit cost for noisy hardware, and they reported the characteristic sign-dependent asymmetry expected in the wormhole-inspired protocol, although hardware noise prevented perfect agreement with ideal numerical simulations. Because that result is currently a preprint rather than an established observational discovery, it should be treated as ongoing research rather than a final verdict on laboratory wormholes. That progression is useful. The first question was whether the theoretical mapping could be written down, then whether a teleportation protocol could represent traversal, then whether a small quantum processor could implement the relevant dynamics. Now, researchers can argue about which signatures genuinely distinguish holographic wormhole behavior from ordinary many-body teleportation, how robust the simulations are to noise, and how much information such a quantum channel could carry. Those are signs of a field becoming more precise. They are not signs that airports will soon offer wormhole boarding gates. There is another reason this matters for our larger question. These quantum computing results demonstrate that a wormhole does not have to be understood only as a large classical tube held open by a mysterious pile of negative energy material. In some controlled theoretical settings, traversability emerges from quantum interactions between entangled systems. Negative energy appears as part of the quantum dynamics. Information transmission can be calculated. The process can be related to teleportation, and portions of that behavior can be recreated in laboratory quantum systems. That is a genuine advance from the older picture. But we now have to make a very large jump back to astronomy. A holographic wormhole represented by a handful of qubits in a carefully engineered quantum processor is not the same thing as an astrophysical wormhole large enough to transmit gravitational waves between different regions of space-time. The laboratory system does not prove that nature builds macroscopic wormholes. It does not tell us that one exists somewhere in the universe, and it certainly does not tell us that GW190521 came through 1. What it does is remove one overly simple objection. We can no longer say that the idea of information crossing a wormhole is meaningless in every serious theory. There are consistent quantum gravitational models in which information transmission through a traversable wormhole has a precise description. There are quantum protocols that reproduce that behavior. There are laboratory systems capable of implementing simplified versions of those protocols. The problem is scaling the idea from controlled quantum models to the actual universe. An astrophysical wormhole would need to form somehow. It would need a suitable geometry. It would need to survive disturbances. Its mouths would need to exist in physically meaningful regions. Gravitational waves would need to propagate through it in a predictable way, and that propagation would have to leave an observational signature distinguishable from all the ordinary things black holes can already do. GW190521 gives us an unusual opportunity, because we have a real signal against which one such speculative model can be tested. We know when the signal reached the detectors. We know its waveform. We know how well ordinary binary black hole models reproduce it, and we can calculate what a proposed wormhole echo would look like and compare the two. That is a very different situation from the quantum processor experiment. In the processor, researchers deliberately construct the quantum system and control the operations. With GW190521, nature has handed us an unknown system and asked us to work backward. The quantum computer begins with the model. Astronomy begins with the signal. So after all of that, after Einstein-Rosen bridges, negative energy, quantum entanglement, traversable wormholes, and quantum computers behaving in ways that can be described using wormhole geometry, we can finally return to the question we started with. Have we found a real wormhole? At the moment, the answer is no. GW190521 is not confirmed evidence of a wormhole. It is not proof that another universe exists on the other side of a space-time throat, and it is certainly not evidence that somewhere, very far from here, another civilization has accidentally dropped a black hole merger through the cosmic plumbing. The conventional explanation remains better. GW190521 is still most naturally interpreted as a merger between two extremely massive black holes. The original LIGO Virgo analysis found that a quasi-circular binary black hole merger provided a consistent description of the observed gravitational wave signal. Under that interpretation, the two black holes had estimated source frame masses of about 85 and 66 times the mass of the Sun, and they formed a remnant of roughly 142 solar masses. That final object falls into the intermediate mass black hole range, which was one of the reasons the detection attracted so much attention in the first place. LIGO described the remnant as the first clear gravitational wave detection of an intermediate mass black hole. Nothing about that interpretation requires a wormhole. Nothing requires another universe. Nothing requires us to rewrite general relativity. And when the specific wormhole echo hypothesis was compared directly with the standard binary black hole model, the ordinary explanation came out ahead. The wormhole study, published in the Journal of Cosmology and Astroparticle Physics in March 2026, found that its echo model could produce a network signal-to-noise ratio comparable to the standard merger interpretation, but Bayesian model selection favoured the binary black hole explanation, with a reported log Bayes factor of about -2.9 for the wormhole model relative to the BBH model. If you convert that particular evidence ratio into less statistical language, it means that under the models and assumptions used in that comparison, the binary black hole model received roughly 18 times more statistical evidence than the wormhole model. That does not mean 18 scientists voted for black holes, and one scientist arrived wearing a wormhole t-shirt. Bayesian evidence is comparing how successfully the models account for the data while averaging over their allowed parameters, but it gives us a useful sense of where things stand. The wormhole explanation survived the comparison, it did not win it, and those two statements should stay together. It is tempting to focus only on the first one because a sentence beginning with "a wormhole model can fit a real gravitational wave signal" is considerably more exciting than a sentence beginning with "the standard black hole merger still works better." But science is not particularly interested in which sentence gets the better thumbnail. What matters is which explanation handles the evidence best. Right now, that is the black hole merger. The reason the wormhole idea remains interesting is not because GW 190521 demands it. It is because GW 190521 allows it to be tested. That is a much more modest claim, but scientifically it is an important one. For most of the history of wormhole physics, there was no astronomical dataset sitting on a computer that researchers could take a wormhole waveform and compare against. You could study the geometry, you could study stability, you could calculate exotic stress energy, you could debate whether quantum mechanics might make some kind of throat traversable. But there was no real candidate gravitational wave event saying, "Alright, show me what your wormhole actually predicts." GW 190521 provides that opportunity. The proposal begins by treating the signal differently from the standard interpretation. Under the ordinary picture, the entire system existed in the region of our universe from which gravitational waves could eventually reach us. Two black holes orbited one another. The inspiral occurred. The objects merged. The final black hole rang down. Because the total mass was so large, most of the earlier inspiral occurred at frequencies where ground-based detectors had limited sensitivity, leaving us mainly with the short merger-dominated part of the signal. That is already enough to explain why GW 190521 looked unusual. The wormhole proposal changes the location of the original merger. In that scenario, two black holes merge in another region, described by the authors as another universe, and the post-merger remnant is associated with a wormhole connected to ours. The ring-down disturbance passes through the throat. What arrives here is not the complete inspiral, merger, and ring-down sequence. We receive a single echo-like pulse. That naturally gives the model one appealing feature. It explains why we would see a short signal without observing the long inspiral that originally produced the merger. We did not miss the inspiral because it was too low in frequency. We missed it because it happened somewhere that was not directly visible from our side of the wormhole. That is an elegant story. But an elegant story has to compete with a simpler one. And the simpler one says the binary was simply very massive. That matters because extraordinary explanations have a cost. If you want GW 190521 to be an ordinary black hole merger, you need two large black holes in an unusual system. We already have astrophysical mechanisms that might create unusually massive black holes, including previous mergers in dense environments. The original LIGO Virgo analysis itself discussed the possibility that the masses could have arisen through hierarchical black hole mergers or other unusual formation channels. If you want GW 190521 to be a wormhole echo, you need considerably more. You need the original black hole merger. You need the appropriate remnant geometry. You need a wormhole. You need the throat to be capable of transmitting the disturbance. You need the structure to remain sufficiently stable. You need the waveform emerging on our side to resemble GW 190521. And somewhere underneath all of that, you still need a physically convincing explanation for how the wormhole formed and what supports it. It is a little like explaining a missing parcel. One explanation says the delivery driver left it behind the wrong gate. Another says the parcel entered a hidden tunnel, connecting your garden to a second universe. You should certainly investigate the tunnel if you find evidence for one, but perhaps check behind the gate first. This principle does not mean scientists automatically reject strange ideas. If they did, black holes themselves would have had a difficult career. Quantum mechanics would not have done especially well either. The point is that a strange explanation earns its place by explaining something the ordinary explanation cannot, or by predicting something new that later observations confirm. GW 190521 does not yet provide that decisive advantage. The signal's short duration is unusual but not inexplicable. Its inferred masses are unusual but not impossible. Its lack of a clearly identifiable long inspiral limits our information, but that limitation is expected for such a massive system. And analyses of the event have explored other conventional possibilities involving precession, eccentricity, unusual dynamical formation, and related effects. A wormhole is therefore entering a crowded room. It does not merely have to fit the signal. It has to eventually distinguish itself from everything else that can fit the signal. That is where future gravitational wave observations become important. Imagine that astronomers detect another event similar to GW 190521. It is extremely short. It looks dominated by a merger or ring-down pulse. There is little obvious inspiral. By itself, that still does not establish anything exotic. Then another appears, then another. Now researchers have a population. They can begin asking whether the events share properties predicted by a wormhole model. Perhaps the pulse shapes follow a particular relationship. Perhaps their frequencies, decay times, or delayed structures behave differently from ordinary black hole mergers. Perhaps improved detectors should have seen the inspiral, but repeatedly failed to find one. Perhaps multiple echoes appear with delays that correspond to a particular wormhole geometry. Those would be much more interesting clues. A model becomes powerful when it tells you not only what has already happened, but what you should expect next. The wormhole echo idea has already begun to be applied beyond GW 190521. In February 2026, some of the same researchers posted an analysis of another short-duration gravitational wave event, GW 231123. Using a related single-pulse echo framework, they reported that the echo model was modestly favoured over their binary black hole baseline for that event, unlike the result for GW 190521. The study is currently a preprint, so it should not be treated as a confirmed wormhole detection or as an established result, but it shows how the hypothesis can be carried from one event to another rather than being invented solely to fit GW 190521. And this is where things become genuinely useful. One unusual event can inspire almost anything. A repeatable test across many events is much harder to fool. Suppose the same wormhole model eventually performs well on 10 unusual signals, then 20. Suppose it predicts waveform features before they are found. Suppose those features repeatedly appear. Suppose ordinary black hole models struggle to reproduce them without increasingly complicated assumptions. At that point, the wormhole explanation would become far more difficult to dismiss. On the other hand, suppose improved observations give us longer inspirals for these systems. Suppose eccentric and precessing black hole models account for the unusual waveforms. Suppose the proposed echo signatures disappear when detector noise is better understood. Suppose increasingly precise Bayesian comparisons strongly favour ordinary mergers. Then the wormhole hypothesis will become less plausible. Both outcomes are useful. That is the advantage of making the strange idea quantitative. It becomes capable of failing. There are many wormhole ideas that cannot currently be tested this way. A person can always imagine a wormhole hidden somewhere with exactly the properties required to avoid detection. Perhaps it produces no gravitational effects. Perhaps it reflects no light. Perhaps nothing approaches it. Perhaps it connects to a region we cannot observe. Such an object may be entertaining to discuss, but it is scientifically difficult to do much with. The gravitational wave version is better because it risks being wrong. It predicts a waveform. Waveforms can be compared. Data can reject them. That is science behaving properly, even when the subject sounds like science fiction. There is another reason. GW190521 is valuable. Gravitational waves allow us to study spacetime directly in a way electromagnetic astronomy cannot. A telescope usually observes light emitted, absorbed, or scattered by matter. LIGO and Virgo measure distortions of spacetime itself. That makes gravitational waves especially suited to testing compact objects whose important differences lie in their geometry, rather than in the type of glowing material surrounding them. A black hole and a wormhole might look similar from far away. Their gravitational fields could potentially produce similar orbital behavior. Some wormhole models can mimic several properties normally associated with black holes, but if their internal boundary conditions differ, the way they respond to a strong gravitational disturbance can differ too. The late-time signal becomes especially interesting. For an ordinary black hole, the remnant settles through the expected quasi-normal ringing of the horizon-containing Kerr geometry. A wormhole may provide another path. Radiation can interact with the throat. Part of it may be transmitted. Part of it may be reflected or delayed depending on the model. The final waveform may contain structures absent from an ordinary black hole ring-down. That is why echoes have received attention well beyond this particular wormhole proposal. Researchers have previously searched GW190521 for other kinds of speculative post-merger echoes associated with possible departures from ordinary black hole horizons. Those claims have not produced a generally accepted detection of new horizon physics, but they demonstrate how the exceptionally massive ring-down heavy event has become a testing ground for unconventional models. This also gives us a useful way to separate three very different statements. The first statement is that wormholes are mathematically studied in gravitational physics. That is unquestionably true. The second is that some theoretically consistent quantum gravity constructions contain traversable wormhole behavior and allow information to pass through. That is also true within those specific models. The third statement is that a macroscopic astrophysical wormhole exists in our universe and has been detected. We have not established that. Those statements sometimes get compressed into one because the word wormhole appears in all three. But moving from one to the next involves enormous steps. A quantum processor implementing dynamics with a wormhole interpretation does not prove that astronomical wormholes exist. A gravitational wave model fitting a signal does not prove that the signal came through a wormhole, and a solution of Einstein's equations does not prove that nature knows how to manufacture the required object. This is why GW190521 sits in such an interesting middle ground. It is not evidence strong enough to claim a discovery, but it is real enough to make the theoretical question measurable. There is a large difference between saying, perhaps another universe could produce an echo through a wormhole, and saying, here is the predicted waveform, here is the detector data, here is the statistical comparison. The second statement can be improved. It can be challenged. Someone can build a better waveform. Someone can include additional physical effects. Someone can analyze more events. Someone can show that the model fails. Or, much more surprisingly, someone might find that it keeps working. That is how something as radical as a wormhole would eventually have to enter observational physics. Probably not with a photograph. Probably not with a spacecraft flying into a glowing circle. And almost certainly not with someone appearing in a laboratory claiming to have arrived from Tuesday. It would begin with small inconsistencies, signals that do not fit quite as well as expected, Repeated patterns, competing models, increasingly precise measurements, and years of researchers attempting to prove one another wrong. If the wormhole survives that process, then things become interesting. This is often how science deals with extraordinary objects. Black holes were once mathematical oddities too. Einstein's equations allowed them long before anyone had compelling observational evidence that astrophysical black holes existed. Over time, observations of compact objects, stellar motions, accretion systems, gravitational waves, and eventually horizon-scale imaging made the black hole interpretation increasingly difficult to avoid. Wormholes are nowhere near that stage. We do not have a population. We do not have a unique signature. We do not have an observed throat. We do not have evidence that the exotic or quantum conditions required for a macroscopic, traversable structure occur naturally, and GW 190521 does not change those facts. What it changes is the conversation. The question, what would a wormhole look like, can now include gravitational wave data. That is a meaningful improvement. If we imagine the strongest possible future case, we would want several lines of evidence to agree. A candidate compact object might produce unusual gravitational lensing. Objects orbiting it might reveal deviations from ordinary black hole geometry. Its gravitational wave response could show consistent ecostructures. Perhaps separate observations would indicate two regions interacting in a way ordinary spacetime does not allow. Theoretical models would need to predict all of those effects from the same geometry rather than using one model for each observation. And researchers would have to eliminate more mundane explanations. Only then would the words real wormhole begin to feel justified. For GW 190521 alone, we are nowhere close. The standard explanation still asks for less and explains more. Two black holes, very large ones admittedly, a short signal because of their enormous total mass, a merger, a ring down, an intermediate mass remnant. That picture is unusual enough without adding another universe. But perhaps that is what makes the event so useful. If GW 190521 had been completely impossible to explain using known physics, the temptation to declare something revolutionary would have been enormous. Instead, we have a better scientific situation. There is a strong ordinary explanation. There is a strange alternative. Both can be calculated, both can be compared with the same data, and the strange alternative currently loses. That is exactly how a serious search for extraordinary physics should begin. Not with certainty, with competition. There is something else worth remembering before we leave this signal behind. Gravitational wave astronomy is still very young. The first direct detection happened in 2015. GW 190521 reached Earth in 2019 and was announced the following year. We have had only a small amount of time, by astronomical standards, to learn what the gravitational wave universe contains. The first generations of detectors have already revealed black holes heavier than many researchers expected, mergers in unusual mass ranges, neutron-star collisions, and a population of compact binaries that continues to test models of how these systems form. There is no reason to assume that every strange signal must involve new fundamental physics. There's also no reason to assume we have already encountered every kind of object nature can produce. Those two ideas can coexist comfortably. Most mysteries eventually receive ordinary explanations. Occasionally one does not. The difficult part is telling the difference. GW 190521 remains on the ordinary side of that line. The evidence still favours a binary black hole merger. But now we know something we did not know when gravitational wave astronomy began. If wormholes exist and if they interact with gravitational radiation, in some of the ways theorists have calculated, we may not need to travel to one to discover it. We may be able to hear what it does. A merger could occur in a region we cannot observe directly. A gravitational disturbance could interact with an unusual space-time geometry. A pulse could reach our detectors. And if the waveform carries the right structure, repeated with the right consistency, and resisting every ordinary explanation we can throw at it, then a machine built on Earth might eventually tell us that spacetime contains a connection we never expected to find. GW190521 is not that discovery. But it may be an early example of how such a discovery would be tested, and that brings us back to the brief disturbance that started tonight's journey. For only a tiny fraction of a second, detectors on Earth registered space-time changing. The most likely cause was two enormous black holes reaching the end of their orbit and becoming one. That explanation is already extraordinary. Two objects with a combined source mass of around 150 suns collided billions of years ago, radiating enough energy into the geometry of space-time for instruments on a distant planet to reconstruct the event long after the source itself had disappeared into a new black hole. Then physicists looked at that small piece of data and asked whether the same signal could test an idea first hinted at by equations written almost a century earlier. A bridge, a throat, a connection between regions that ordinary travel cannot join, perhaps even a connection between what we would naturally describe as different universes. The answer, for now, is that the data do not require it. But they allow us to ask, and sometimes that is the first useful step. We began tonight with a gravitational wave signal that seemed to arrive without much warning. We followed it backward into black hole mergers, through the missing inspiral, into curved space-time Einstein-Rosen bridges, exotic matter, quantum entanglement, and quantum computers. And after all of that, we have ended up somewhere reassuringly scientific. We do not know of a real astrophysical wormhole. We have not proved that information from another universe reached Earth. The strongest explanation for GW190521 remains a massive black hole merger. But wormholes have moved at least a little closer to the world of testable ideas. They are no longer only drawings of folded paper or convenient devices for getting fictional spacecraft across a galaxy before the credits. Physicists can calculate how they might affect gravitational waves. They can compare those calculations with real data, and future observations can make the hypothesis better or worse. That is considerably more interesting than simply believing in wormholes because we would like them to exist. So if you're still awake, consider the detector for a moment. Kilometre-long arms, lasers moving between mirrors, an instrument waiting for changes in distance smaller than anything our senses could possibly notice. Most of the time, nothing dramatic happens. Then space-time shifts. A signal appears. Scientists compare it with thousands of possible waveforms. Usually the answer is something we already understand reasonably well. Two black holes, two neutron stars, a compact system obeying general relativity. But hidden somewhere among future signals could be something that refuses to settle into those categories. If that happens, researchers will test ordinary explanations first. They will argue about noise. They will improve the models. They will check the detectors. They will analyze the event again. And only after the less dramatic possibilities have been exhausted will anyone have earned the right to say that perhaps the geometry itself is stranger than we thought. Until then, GW190521 remains what it has been since it was detected, a very unusual gravitational wave, a very massive black hole merger candidate, and an unexpectedly useful place to ask one of the strangest questions available to modern physics. If this slow journey through black holes, wormholes, and quantum information has given your mind something interesting to settle around while the rest of you gets ready for sleep, you can leave a like and subscribe to Science for Sleep. It helps these longer explorations find other people who enjoy discovering just how complicated the universe becomes when nobody is in a hurry. And before you drift away, you can leave one answer in the comments. If a future detector really did find convincing evidence of a wormhole, where would you hope the other side leads? Somewhere else in our galaxy? A region billions of light years away? Or, if nature is feeling particularly ambitious, somewhere that does not belong to our universe at all? For now, there is no need to decide. GW190521 has given us enough to think about without asking you to choose a destination. The ordinary explanation is still winning. The wormhole remains hypothetical, And somewhere beyond our planet, black holes continue to orbit, merge, and send faint distortions across space-time, leaving us to work out what made them only after those signals finally reach Earth. Sleep well, and if the universe does happen to contain shortcuts, perhaps we can leave finding the entrance until morning.